So, good afternoon, everybody. All ready to start? So, good afternoon, everybody. For those of you who don't know me, I'm Joe Flanagan, the project manager for the Energy House 2. We're well on the way now with our construction. Everything seems to be going to plan. You can see the background there. I've not updated it from last week, but yeah, things are moving apace. And welcome to our latest in the series of retrofit workshops. Today we're going to be talking about low carbon heating. So we've got some very interesting speakers here. We're going to have an introduction to low carbon heat. We're going to hear about heat pumps, air source and ground source with some very practical experience, practical case studies, district heating, and finally round off with other low carbon technologies. I'll just remind you of the kind of housekeeping rules. Please keep yourselves on mute. We will be recording this, so if you don't want to be seen, turn the camera off. If you want any questions, please submit them in the chat and we'll for those as we go along. And if you've got any other issues, kind of technical things, just direct message Ruth, who's organising all this for us today. So without any more delay, I shall hand over to my colleague Nigel Blanford, who's going to give you a bit of an introductory talk around low carbon heat. Thank you.
You're just on mute, Nigel. Hey, Nigel, can you hear me? You're just on mute.
Can you hear me now? Hello.
Yes, can hear you now.
Thank you. Great. Sorry about that. I was just going to sort of reiterate some of the things that that Joe said, but I won't. The only thing that I will reiterate is that there's probably some technical hitches because we're still very new at this, and that was a point in case there. Can you all see the screen I'm sharing? Is it all in? Great. Thank you very much. So, like I say, this is all about low carbon heat. I'm going to give you a brief introduction now, an overview on the policy surrounding low carbon heat before we move into the speakers. So first of all, if you can see this is the UK emissions by sector in 2016. So the inner circle there, you can see the overall emissions by sector, and you can see that heat forms 37% of that. And if you go into that outer ring, you can see that space heating and cooling is 17%. If we home in on that a little closer, what you can see, this is a slightly different metric. This is fuel consumption for heat in 2017, is that the largest proportion of that is domestic space heating. So this is why it's really important in this whole retrofit environment. We've got to tackle this as part of the sort of carbon emissions. And again, if we look at where that heating is coming from at present, you can see that gas central heating forms about 85% of that. And at the moment, you know, the 15% are divided up between other sectors at the moment. That's obviously not really where we want to be. We want to be somewhere else. And if we look at areas in the UK off of the gas grid, the dark blue areas are off of the gas grid. So while it might look like there's large areas off of the gas grid, the population is quite small. So I'm saying there's about 80 to 85% penetration of heating in the UK domestic market. So gas's final consumption for space heating in 2018. There's a table for Europe. You can see within there that you know, the EU average 27 is 38%. We are at 75%. I think the only people that come anywhere near as close to that are the Dutch, and we'll see a little bit why that is in the future. But why have we got this like large dependence on gas? Well, it goes back to the fact that sort of, I guess, during the Industrial Revolution, we had, and what drove the Industrial Revolution in the UK was coal. We had plentiful amounts of coal, and that wasn't just used as a solid heating fuel, that was gasified and turned into a gas, and we began to develop our gas network. Now, obviously, we switched from this coal gas to what we would call, I say, North Sea gas. And if we look here, the amber area is the sort of natural gas fields for the North Sea, and you can see that it's ourselves and the Dutch that are blessed with large areas of gas, and that sort of accounts for ourselves and the Dutch heavy use of gas. Gas prices for household consumers. We can see here the UK. If we draw a line straight across to somewhere that's kind of equal, what we can see, that's Belgium. This puts approximately, this is in euros, I converted it, but this puts approximately the price of the UK at 4.3 pence a kilowatt hour, making it the cheapest gas price in Western Europe. So everything between Belgium and the UK on that graph is basically Eastern European countries. And if we look at, like I'm saying, the Dutch, they're right over the far side. They've got the most, even though they've got good access to gas, they've got expensive gas. So it's around about, 10 cents. So let's say 10 pence. It's considerably more price than ourselves. If we actually look at sort of gas prices, though, and I've pulled some up here from a gas comparison site a little while ago, you can see that, I don't think I'm paying more than 3 pence a kilowatt hour for my gas, so it's quite cheap. And gas has basically been king. But as far back as 2013, the government's Future of Heating document publication, the government was leaning towards the use of heat pumps and in high density urban areas, heat networks. So this is the beginning of the formulation of this policy, this change that we're seeing. Future Home Standard 2019 consultation, again, not only is it sort of pushing towards the heat pump side, but also you have to demonstrate that the costs, there's an affordability rating, that costs will have to be low for that heating as well. More policy, Clean Go strategy sets out proposals for taking the agenda forward during the 2020s, and a key plank of that is heating, because we've seen from the stats that heating is pretty vital if we're going to drive down our carbon emissions. In the Chancellor's spring statement in 2019, he noted the mandating the end of fossil fuel heating systems in all new homes by 2025, and that kind of direction was being pushed, particularly in areas off of the gas grid, to say that no new homes off of the gas grid will be heated with oil or LPG in the early 2020s. A lot of these things get pushed slightly back, but this is the trajectory that we are moving on. So, a lot of the the webinars up until now have been looking at sort of building fabric measures, but we still have to heat the building. But you can see that we have those building fabric measures have been successful, and we have seen a decline in the use of energy in our homes. This work has been, I guess, driven by things like the energy company obligation, the Green Homes Grant, rest in peace, and also the domestic renewable heat incentive. So this is from Ofgem, February 2021, and this is the deployment of heating technologies under the domestic renewable heat incentive, and you can see that. So I guess from the start, we've seen a rapid growth in biomass, which has leveled off, but a continual growth in air source heat pumps. So there's been around about 10,000 air source heat pumps installed each year under the domestic RHI. The government has set a target for 600,000 heat pumps a year by 2028. That's pretty tough, considering that, like I'm saying, 23 million residential buildings. That's great. Greater than 8% of households are heated by gas at the moment. If you do the maths, I think what we find out is that we're going to need bigger carrots and larger sticks. However, government policy is still concentrated on electrification of the heating and heat networks in dense urban areas, and that's the way we will be going. Thank you very much for that. And if we've got any questions, I will take them now. Right, I see we've got one question up in the chat box there. It just says, Peter Jones, Peter to everyone, Peter Jones. Okay, any other questions? Someone said, what about hydrogen? We will be covering that later. So that's up to me to talk about hydrogen later. And I think this is the topic that will begin to stimulate a little bit of discussion, but I think we can leave that until later. I know certainly that David Kemp and Nathan will want to jump in on that conversation when we come to it. Nuclear, yes, I guess there is nuclear as well. That's, I guess, under the electrification. We're not going to have small scale nuclear plants in our homes, I guess. So I guess you could have, or you do have in some countries, heat networks using the hot water from nuclear, but yeah, it's a low carbon energy technology, less so a low carbon heat technology. Right, if we have got no more, yes, so yes, one thing we're going to do first of all, if we could do now, we do a little poll actually. So if you want to put the poll up on the screen so everyone can see. So the first question is, what would you say your knowledge of low carbon heat is at the moment? So very good to I know nothing. And the second question is, what would you say your knowledge of low carbon heat technologies are? So one's around the policy and one's around the technology. So if I could ask you all to do that, and can we, if there's enough, can we share the results, please? So, oh, it's quite interesting. So policy is on the fair to poor side, and the technologies is on the probably the fair side as well. So hopefully we'll all gain something. We'll be doing the poll again towards the end of this session. And see whether you've improved anything. So that's very interesting results here. So without further ado, we will move on to our next speaker. So our next speaker is the award-winning Nathan Van Gablin. Comes from a family background in heating. His father, grandfather and great uncle all had careers in energy and heating. While he's a qualified heating engineer and plumber, Nathan now concentrates on training. His company, Better Talk, is the recent winner of the British Renewable Energy Awards 2020 Communications category. Like I said, he's deeply embedded in heating. I'm sure he knows the delta T of his blood between the coming in and going out of his heart. That's how much he's deeply ingrained in it. So he's going to put on, we're going to put on a little pre-recorded video, and then we'll have questions after that. So thank you. Take it away, Ruth.
Which end do you think water would come out of this pipe if I'd filled it with some water? Would it be this top end or would it be this bottom end? I guess it's the bottom end. So the law of gravity dictates that water will flow from a high place to a lower place unless we pump it uphill. And it's the same with heat. Heat travels from a high place to a low place. So that's a high energy state to a low energy state, or a higher temperature to a lower temperature. So when you're in your lounge, it's winter and you're nice and cozy, you're in your lounge, the air temperature is 21 degrees. That 21 degrees is trying to get outside to the 10 degrees or 7 degrees or whatever it is outside. Heat moves from a high place to a low place, unless, like the water, we pump it. My name's Nathan Gamblin, and I'm here to talk to you about heat pumps today. You can find me on betateach.co.uk, where I also run a podcast about renewables called Beta Talk, but you'll be able to find that at this place. Here we go. So we're going to talk about the different types of heat pump. We're going to talk about how they work. We're going to talk about any issues with how they work. We're going to talk about their efficiency. But first, I just want to talk a little bit about temperature again. So I want to talk temperature. So here in the middle, we've got degrees centigrade, degrees Celsius. Here over on the right, we've got what our North American cousins would use, so Fahrenheit. And here we have Kelvin. So arguably, there's actually no such thing as cold. So I know we would feel cold at 0 degrees Celsius. That's obviously when water turns to solid. But there's astronomical amounts of energy at 0, astronomical amounts of heat energy. There's different types of energy. There's chemical energy, light energy, heat is energy as well. And what does that mean? Well, everything's made up of atoms and molecules, and they're all moving around. They will only ever stop moving around at minus 273 degrees Celsius, which is absolute 0 in Kelvin scale. So no one's ever got down to this. I think they got pretty close in a laboratory, but at this temperature, everything stops moving. Arguably, that's when it's cold, but everything else has heat energy. So even 1 degree Kelvin or minus 272 would have energy. Your molecules will be moving around, albeit very, very slowly. And the amount they move around, so energy is measured in joules, kilojoules, and the amount these molecules are moving around, their velocity, is what temperature is a measurement of. So like we would measure the velocity of a car miles per hour, its speed, we measure the speed or the average speed of molecules is temperature. So the higher the temperature, the more they're whizzing around basically. So around here, so we've got 0 degrees here. Let's say that our outside temperature is 0. And remember, with a heat pump, we can move things uphill. So we can move energy uphill. So we could move it from 0 degrees up to, well, it's got 27 as approximate room temperature. You wouldn't really want your room at that temperature. That'd be quite hot. But we could move energy from 0 into our room of around 21. Is what we usually have it. And there's not a lot of difference in the grand scheme of things between 0 and 21 degrees if you want to come all the way down here. So there's loads of energy to use. And refrigerants, they will boil at a lower temperature. So what we're using at the moment, we're using R32 is a very common one now. So we'll replace 410A. We've got R290. Now they're going to be, I think R290 boils around minus 40, minus 42. I think R32 boils at around minus 51. And we'll talk about their boiling temperatures a little bit when we talk about how heat pumps work. So yeah, just wanted you to get an idea of temperature. Just because we think something's cold, it has masses of energy. It really, really does have a lot of energy. So let's talk about the different sorts of heat pump you can get. So air source heat pumps, I've used a little acronym here, ASHP, and you can get different types of air source heat pump. You can get air to air and air to water. Now when we say the word source, that's where the heat energy is coming from. So in this instance, it's coming from the energy in our air. So remember, even if it's 2 degrees or 5 degrees, I think between 2 and 5 degrees is going to be the average temperature over winter. On the very, very, very coldest day, or what we call design temperature, we will design heating systems around about minus 3. Now, of course, it can go lower than that, especially at night. 2010 got way down. but we don't tend to design, it'll be silly to design our heating systems to meet the worst ever possible temperature. So we take the average worst temperature, and that's around about -3. That's what we call design temperature. Now, most of our winter's never going to be anywhere near that cold. It's going to be around about 2 to 5, I think, and that's got lots of useful energy. And so we've got these outdoor machines, and they're kind of sucking in all this air, about a cubic meter of air a second, and that's got all this energy in it, all this heat energy. So that's source. You'll hear the word source and sink. So source is where you're getting the energy from. The sink is where you're delivering it to, and that might be your radiators, it might be your underfloor heating. That's your sink. So air source heat pump, you've got air to air. So our source is the air, but rather than heating up via a heat exchanger, heating up water to flow around our radiators or underfloor heating, we are literally heating up air and blowing it out. So this is a bit like your aircon units, comfort cool units you'll have in your offices and stuff. And then we've got air to water. So once again, we take the source is the air, that's where we're getting the energy from, and we're exchanging that heat to water that will run around our radiators and our underfloor heating. We call them emitters. We've then got ground source heat pumps, and they kind of sort of tally up with water source heat pumps as well. So ground source, in America, you'll sometimes hear them refer to geothermal. We don't tend to use that term. We do, but we use it for a different entity. So most of the heat we're extracting from the ground is solar energy. Same with the air. So the heat in the air that we're actually extracting up here, our source, that's solar energy. It was the sun that made that air warm. With ground, it's the same thing. So the solar energy that's warmed that ground up, and we extract that energy. But of course, you go out to places like Iceland, they've got these thermal pools. You know, that heat is actually coming from the center of the earth kind of thing, or from volcanic activity. That's what we would call geothermal. I think the Americans were sort of, they group all ground source into geothermal, I think. So ground source is mainly from the heat in the ground. And we can also extract heat from the water sources that we've got on our ground as well. So that's a river. We can also extract it from the sea. So we can extract the heat energy from the sea and water bodies. Now, the advantages of ground source and water sources, we've got, they're maintaining constant temperatures. Of course, with air, you know, the fluctuation between of temperature over the course of the winter is a lot greater. So that has advantages and disadvantages. You know, you're going to get a constant temperature of around about, let's say, 5 degrees, and Andy will be able to discuss that more with you in his presentation. But an advantage of air source is, you know, the days when it's on 10 degrees, 12 degrees, obviously your heat pump can run a lot more efficiently. Now, one thing I should say is that heat pumps aren't new. So you can't really see this. This is from a book I've got. It's of a heat pump that was in Norwich, the city I grew up, built in 1948, and it took heat from the river. Here is the back of my Tesco's. They're literally everywhere, in shops, supermarkets. So the ones you can see here, they're pulling heat in from the air to heat the actual room inside. I mean, it's used all over the world for refrigeration of food. So here's the ones that are actually they're now pushing heat out into the air, because they're connected to all the refrigeration inside the supermarkets. But you're going to see wall-mounted units like this in offices, pubs, clubs. I mean, they literally are everywhere. I mean, there's more heat pumps in this world than boilers, put it like that. You'll often see in offices the cassettes that we put up into ceilings. I'm sure some of you have been in offices and looked up, or been in certain places where you've seen these, and these heat and cool your buildings. They're not new. Just to stress the point how ubiquitous heat pumps are. I mean, they are literally everywhere. This is my local plumb centre, my local Wolsey. Plumb centre are the biggest merchants of gas boilers in the UK. Bearing in mind we sell 1.7 million a year, and even they heat up their staff with heat pumps. And you'll possibly see that building hasn't been hysterically insulated to get these things to work, which is something we'll talk about in a bit. Here you'll see, this is my cousin's bedroom. He's been working with heat pump technology for over 40 years. I think his 2 apprentices slung this one up. That's a 4 kilowatt indoor unit. There's a closer look at it. Yeah, it was his apprentices, because I can see the hole at the bottom where the pipes are coming in. But you know, 250, 300 quid for that indoor unit. That's probably about 4 kilowatt. He'll have an outside unit, which you'll probably see in a minute. There's the fan off, the fan cover off. The outside unit, what's it, 4 kilowatts, probably about 580 from a cousin. So air to air can be relatively cheap. It's an option. It's not for everyone. It can also cool you in the summer. So I think he's got RAS system, but I mean, he could have that 4 kilowatt on, even though it's upstairs. That's definitely heating up all his upstairs, and even going downstairs. He's got no doors downstairs. So there's the outside unit. A lot of people don't probably realise how low a heating demand. I know we talk about we have got leaky homes, but they're definitely not 30 kilowatts. We're sticking 30 kilowatt boilers in homes with sort of an average heat loss around 6 kilowatts to 10. So your gas boiler is about 4 times oversized. I mean, we're sticking 30 kilowatt boilers into 3-4 bed homes. 30 kilowatt boiler will do a 30 bedroom home. So the heat pumps that we use tend to be properly sized. We'll talk about that when we come to talk about any issues with their use. We're going to now talk about how they work, but I don't want to labour the point of how they work. It can get quite complex, and there's going to be some great stuff on YouTube. If you want to look on YouTube, look up things like the vapor compression cycle or the refrigeration cycle. But let's have a look a little bit. Let's have a recap, and let's then have a look a little bit how they work. So let's have a little recap. We've talked about how heat moves from a higher temp to a lower temp, a bit like how the water was flowing from a higher place to a lower place. With water, it's gravity. With heat, it's the second law of thermodynamics. You can all look that up if that's something that interests you. We've talked about the different types. Now, you could probably go on forever about different types, but we've split them into air source and ground source. With air source, there's all different sorts. There's split systems, there's multi-splits. We haven't really discussed them. There'll be loads of information online about them. Monoblocks is probably what you're going to hear David talk about. So monoblocks is sort of is probably where we're going with, mainly with the domestic, whether that's retrofit or new build. Monoblocks means everything's outside, so all your refrigeration type of gubbins is all outside, and all that's going indoors is our flow and return primaries to your heating system and your hot water system. Split system would be where you're kind of splitting the refrigeration side of things, but I'm not going to dwell on that too much, otherwise I don't want to confuse you. So we're going to talk about the vapor compression cycle. So basically, I'm not going to talk too much about how heat pumps work, because there's lots of stuff on YouTube, and you can look at it to your heart's content. There's generally 4 main components people talk about. These are your evaporator and condenser. So these are your heat exchangers. I'll show you a picture of a heat exchanger in a minute. You can sometimes think of something like your car radiator. That's a heat exchanger. So let's start. So you've got your refrigeration inside this closed system. It's a hermetically sealed system. Nothing can get in. You definitely don't want anything getting in. That would contaminate it. We have to be very careful about when we put refrigeration into systems. We have to purge it with nitrogen. We then have to evacuate. We use an evac pump to get literally every drop of moisture or anything that's in this sort of circuit down to 2 torr, and then we can put our refrigerant in. So we definitely can't have the refrigerant contaminated. So refrigerants boil, as we said, at a very, very low temperature. So remember, heat moves towards a colder state, so it's hot to cold. So our outside, let's say this is an air source heat pump, our outside air, it might even be 0 degrees Celsius, it's quite capable of putting energy into that refrigerant, which is boiling at -42. Now, it's not going to raise the temperature of that refrigerant. If it did, that would be sensible heat, but it's already hitting boiling point. So it's latent energy. Latent energy is when energy is going into something, but you're not raising the temperature. So it's still an incredible amount of energy going into it. We've got big fans on these outside units, monoblock or split, and they're drawing that air in over the evaporator. They're drawing it in quite quickly. In fact, the fans will be connected electronically to the compressor. So depending on how much heat you need, the fans will will draw it in. Obviously, if it's a warmer day, let's say it's 12 degrees outside, your fan won't be working as hard as if it was 0 degrees. Now, what it's doing, it's boiling this, it boils it into a vapour. So this number 4 is our suction line, what us refrigerant engineers would call a suction line. If you touched it, it's going to be very, very cold, but we call it a low temp vapour. So it's got all the heat energy. It goes into a compressor, which compresses it. And when you reduce volume, all these molecules inside that refrigerant, they've got less space to bump about and move about, so they get hotter and hotter. The analogy that you'll most commonly hear is where if you're using a bicycle pump and you're really going quickly with a bicycle pump, you can actually feel that pump getting hotter. So when you compress that vapor, it gets hotter. You've raised its boiling temperature. So now it comes out at number 1. We're now at a superheated vapor. And what happens now is this is now hotter than our indoor air. Or the water that we want to run around the radiators. Let's say we want to run a 40-degree flow temperature around our radiators. That's a nice temperature. So this is now hotter than that 40 degrees. Remember, hot moves to cold. So whatever the temperature is in here, it's moving to that 40 degrees water. And as it does that, it condenses, it's starting to turn back into a liquid. So here it's kind of liquid and vapor in the same time. And it goes into a metering device. Some people don't like calling it an expansion valve, where it allows that liquid vapor to sort of expand a little bit, and then it will it decreases pressure and it turns back into a liquid to go all the way around the process again. And that's why it's called a cycle. You can look that up, the vapor pressure compression cycle. It's a fantastic bit of science. You can go right down the rabbit hole if you want with the science, and it can get quite complex. But that's basically how it all works. So we've talked about the different types. We've talked about how they work. We're now going to talk about any issues with how they work and heat pump efficiency. So let's start with heat pump efficiency first. So we've got a little slanky diagram here. Now we've got 5 kilowatts of heat coming on. Hopefully you can see that. 5 kilowatts of heat coming in. That could be coming from the ground. That could be coming in from the air. And then we've got 2 kilowatt electrical input coming into the unit. And that's to drive the compressor, the fan, a bit of the controls. Okay, and that gives us a total heat output of 7 kilowatt. So we've got 5 kilowatt coming in from outside, somewhere, ground, river, water, or the air, and we've got 2 kilowatts that's being used to sort of power the unit, power the compressor. Now, if we were to divide this 7 by 2, we get 3.5, and that gives us, and I'm sure you've heard this term, COP, C-O-P, coefficient of performance, and that's the ratio. So it's the ratio of our heat output to what we're putting in electrically. Now, they're super duper efficient, so 3.5 is 350% efficient. If you think about your boiler, I know the boiler manufacturers like to badge their boilers up at being 93% efficient. They're not. Well, very, very, very rare will you get one of the 6,000 boilers going in daily in this country. The trouble is they come out the box with a flow temp of 80 degrees. Unless you know what to do with that and get that down to about 60 flow and 40 return, you're never going to get anywhere near that 93% efficiency. So they're around about 86, 87% efficient. So heat pumps, very, very, very efficient. Up here, it just goes over what we've just said. 5 kilowatt heat extracted from the ground. I'll get the air. Plus your 2 going in, 7 kilowatts of heat. Now, your COP is changing all the time because your compressor is doing different things all the time. It's ramping up, it's ramping down if it's an inverter type. And remember, we talked about the sink and source. So our source temperature, let's say that the sun's come out and the air temperature now is risen. Our system, these are controlled by weather compilation. It knows that air temperature is now higher, and it can meet that by lowering the water temperature we need to go around the rads. So we're narrowing the temperature between our radiator water and the outside air. So if you narrow that delta T between sink and source you'll get a better COP. And of course, if the temperature drops outside, your compressor works harder and it will have to heat up the water a little bit more that's going to be flowing around your radiators, the mean water temperature, we call that. So your COP is changing all the time. So to do an annual representation of its performance, we talk about the SPF, which is the seasonal performance. So the seasonal performance factor is measures it annually your heat output compared to your heat input. Now it's very easy to get hung up on these COPs and seasonal performance factors when of various different machines and products out there. When in essence, this brings us nicely to our final bit. You know, is there any issues with using this stuff? And yes, there is. It's people. The two most important cohorts in all this are the homeowner, the consumer, and the engineers that put these in, the designers and the commissioning engineers and installers. And this is where things can start to get a little bit wrong. So going back to the COPs, your efficiency will always come down to how well these systems have been designed and installed. And unfortunately in the UK, I mean, I'm not a fantastic engineer by any stretch of the imagination. My expertise and speciality really is about how we're training people in this industry. That's what I'm kind of known for. And one of the things I talk about quite often is we train people to be qualified rather than training them to be competent. The qualification industry is very lucrative, and you know, we're talking about thermodynamics, we're talking about hydraulics. It's getting quite technical. Heating's always been technical. It's just that the combi boiler gave us all a get out of education free card, as my friend calls it. So the consumer wants something very easy and simple to operate. That's okay, we can do that. But what they've got to really understand is these do not work like boilers. They're not going on. We're not programming them to be off when they sort of go out for a couple of hours in the evening or day. You know, the heat pumps like to maintain constant equilibrium in this house. They like to maintain that temperature, working with the weather compensation. Compressors do not like going on and off. They really don't like it. No motor actually likes to go on and off, and that's why you find a lot of fan motors break down in gas boilers. I mean, motors are made out of metal. Metals, if they're going on and off, they're expanding and contracting because they get very hot motors, and expand and contract all the time. They get metal fatigue. So you'll find that the most expensive motors. So some, for instance, like my cousin does all the sort of heat removal, air conditioning in post production, and all the top recording studios in this country. All these sound boards, which are sort of computers, lots of little motors in the drives, are kept on 24/7, 365. They don't shut them down. These things like to be kept at constant temperature. Your inverter-driven compressors, they don't want to be completely shut down and on again, completely shut down. And also, unlike a gas boiler, we're not using these very high temperatures. You know, we're not using flames to heat water, so we're using the vapor compression cycle, sort of this low energy. And so we've worked out it's more efficient to keep your system enabled, just working with the weather, what's going on outside. So there's a bit of an education thing there with the consumer as well as the engineers. It's a mindset, because obviously it's natural to think, well, you know, if you've got it shut off, we're saving energy. But of course, if you shut off a heat pump system for a good few hours in the winter, like because you've gone out, when you try and start that up again, you've got to heat this house up to this temperature now with this low temperature heat we're doing. And you'll start putting it all out of whack. The COPs will really drop down. So we just we maintain this nice sort of temperature throughout the home. So we've got to get the engineers trained up. Big problem, and it's a big problem for you people, consumers, homeowners, to know who a good engineer is. That is really a big problem. I mean, the special advisor to the energy secretary realised that, because they got hold of me and said, you know, can we use one of the engineers you use on your podcast? They aren't going to these registration schemes, put it that way, because they don't always guarantee competence, unfortunately. So thank you very much for listening. You can find my podcast at this website, and I'm sure we've got some time for some questions and answers. Thank you.
Okay, I see we've got one question that's come in here from Sarah. She's asking about the size of boilers here. She says combi boilers are sized on hot water demand as well as the heating. So while it might be, you're saying a 30 kilowatt boiler is too big for heating a home, she's saying, well, you have to surely take into account the hot water heating with a combi boiler.
Yeah, that's right. So one of the advantages of a combi boiler was they gave people this option to stick a boiler in, instantaneous hot water, and sort of the rule of thumb was the bigger you go, the quicker you can instantaneously heat that water. Unfortunately, we got to a situation where I wouldn't even say people are sizing it for hot water demand. They kind of just go with the biggest possible to sort of cover all bases. And even with system boilers and conventional boilers, we have found that no one's doing heat loss calculations, and most of them are going to be oversized as well. And of course, you then get cycling situations. I mean, there's some very good boilers on the market, don't get me wrong, and some of them can modulate down with good quality weather compensation, but the consumer won't know which ones they are, and a lot of the engineers don't actually, if I'm honest. Oh, we got another one. So
You're muted again, Nigel.
Oh, sorry. We've got a question here from Richard saying, I'm discovering there are impacts on installers, e.g. underfloor centers have to be 100 millimeters according to polypipe rather than 200 millimeters with conventional. Have you got any thought on that, Nathan?
Yes, so with a lot of the good engineers out there will arguably going to be doing 100 centers. You've increased you've increased your emitter size, and it all means, like I say, if we can get this narrow the delta between source and sink. So one of the best engineers I know, whether they're doing boiler or a heat pump, he will design to a flow temperature of 35 degrees. Now, to some people that sounds, well, how can you have a flow temp going in at 35 degrees? We're keeping our air warm at 21, and it's possible. You do have to calculate mean water temperature. You have to sort of use a lot of factors to sort of get these radiators sized right. Obviously, the advantage with underfloor heating, you've got the whole emitter surface is on your floor, so you haven't got to bang these great big triple rad sort of rads everywhere. But yeah, that's a good advice.
Any more for any more? Message from Ruth. I did direct message you. I don't know whether you've seen that at all. But anyway, okay, we will move on now. Next up, we have David Kemp. David has spent 15 years working in client-facing roles with public and private sector organisations, delivering programs and bespoke projects. He is keen interest in sustainable heating, and his current role at Procure Plus has seen the rollout of heat pumps to the social housing sector. I've worked with Dave for many years and appreciate his advice. So without further ado, David, do you want to take it away? Thank you. Now you're on mute, Dave.
Good job, I was muted then. Everybody hear me now? I'm taking that as a yes. Right, screen hopefully being shared. So let's get it into presentation view. I think the most encouraging thing is when you don't actually contradict the person that's went just before you. And in actual fact, Nathan's reinforced some aspects of my presentation, which is yes, reassuring. So Nigel, can I just get the thumbs up? Is that all on the telly correctly, as it were?
You just still need to put it into presentation mode.
Right, okay. There she blows. Right. We got there in the end. Apologies for that. So right, let's get cracking. As is customary in these circumstances, I've got a little bit of a contents page just to, I suppose, for the benefit of those that aren't watching live and might be looking at these slides at a later date, or just for your own assistance when looking at these things, as I'm sure they're going to be sent out to everybody. So first off, we're going to run through who we are, who's Procure Plus, what we do and all that kind of stuff. And then just quickly cover off the things that I'm not going to talk about in the presentation. It'll make sense in a second. Then run through some heat pump myths. Again,
already mentioned, thankfully, by Nathan, and equally some heat pump truths as well. Before touching on the role of heat pumps in relation to zero carbon housing, specifically from a landlord's perspective, look at some of the past projects that we've been involved in, some of the learning that's come from that, and equally future plans associated with heat pump deployment, again, primarily from a social landlord perspective. So first off, who we are and what we do. Procure Plus, we're a not-for-commercial profit, social housing and public sector focused purchasing and regeneration company. That's a bit of a mouthful. So what we effectively do is manage framework agreements and dynamic purchasing systems and a whole host of other procurement services that social landlords and local authorities access for the delivery of their property investment programs. So yeah, contracts for the supply of goods and the installation of services. The installation services as well. So that's the procure bit. The plus side of thing is the actual real reason we get out of bed in the morning. We effectively want to deliver economic regeneration and community regeneration within those areas, those estates where our landlord customers have got a presence. So effectively, we aggregate demand and volume for products and services. That makes them more cost effective for a public sector buyer to purchase, but we don't pass on 100% of that saving. We top slice a chunk of that, and with that element of saving that we've scalped off, we fund training and employment initiatives in our landlords' communities. So other organisations, a bit like us, they might support the painting of a community centre or planting flowers in a local area. All dead good stuff, and all contributes to regeneration. But as far as we're concerned, you can only really deliver social value. You can only really deliver economic regeneration in an area by getting people into employment, and that's primarily what we do. So, despite COVID last year, we're still feeling the effects of it, obviously. We were able to achieve our pre-lockdown forecast of 125 million quid. So that all came through our frameworks. That generated, we've calculated around about £16 million worth of savings for our customers. Those are the actual cashable savings that they felt in their pockets. But more importantly, it delivered 662 new jobs for those people in the communities where our landlords have got a presence. So that's who we are and that's what we do. Right, so the why not covered. So let's take it as a given that climate change is important and we really should be addressing this stuff. So I'm not going to talk about polar bears. I'm not going to talk about stranded assets. I'm not going to talk about any of these things, and most specifically not fine wine production in Wigan as the temperature increases to the point we can get a Chardonnay grape growing on Bickershaw coal field. We're not touching any of that. It's there. Let's take it as read. So straight into the core of the presentation. And again, this has already been mentioned ably by Nathan and probably more concisely than I'm going to do anyway. But here it goes anyway. Heat pump myths. So let's dispel these from the off. These heat pumps only work in super energy efficient buildings. That's not true. So as long as the whole system can be designed to operate at that lower flow temperature, it'll be fine. Yeah, there are enough 200, 300-year-old solid wall barns, and the National Trust is invested in shed loads of these things. They're going in abbeys and cathedrals up and down the country. They work as long as the entire system can be designed to accommodate that, how those products work with these lower flow temperatures. You have to replace all radiators and you have to oversize everything. So the disruption is going to be immense. Again, not strictly true. So yes, you have to size the radiators and the heat emitters correctly, but some recent BEIS research has demonstrated that the majority, I think it's over 50% of all existing heating systems are technically heat pump ready already from a radiator, from a heat emitter perspective. They were oversized by the original installer. Yeah, you might want to prepare for swapping a few out. You might want to replace some pipework. There's a whole host of stuff around flow rates, which needs to be overcome when you're designing and installing these things. But to assume that we're going to have to rip every single scrap of copper out and replace every single radiator in your dwelling, it's not true. Another one, they will cost more to run because electricity is more expensive than gas. And again, Nathan's quite ably pointed out that gas boilers don't necessarily operate at the efficiencies that they should be operating at already. And the way that landlords and the majority of people, I think, assume or try to calculate what the running costs are going to be. They look at their EPC, what's the energy demand from a particular building, what's the demand for this house. And then they figure it out, 3.5 pence per kilowatt for gas, or 15 pence for the electricity. Or let's look at the numbers. Even with a COP or a SPF, a seasonal performance factor of 3 or 3.5, we're still touch and go as to whether or not it's going to save you money. But again, the way that people tend to calculate these things, they haven't factored in the fact that your boiler isn't operating at 96% efficiency. And I think, again, Energy Savings Trust had done some work recently that demonstrated, I think, the average boiler efficiency for heating was around about 82% from memory. It was even worse than Nathan's projection, because nobody really designs a gas heating system in the same way that an engineer would design a renewable heating system. Likewise, gas meters and standing charges are often left in these things. If the gas boiler was the only thing that you had in your property that burnt gas, you took the gas boiler out, why would you keep the meter? The meter costs, via a standing charge, between 80 and 100 quid a year. If you're removing gas from your property, you remove the meter as well. It doesn't preclude it coming back in at a later date, but it's 100 quid's worth of savings to be had straight away. So it's not guaranteed, it's not a certainty that they will cost more to run. And then the last myth that's often rolled out is that if we all go berserk for heat pumps, we're going to fry the grid. And again, that's not true. I'm privileged enough to sit on Electricity Northwest's Sustainability Advisory Panel. Electricity Northwest being the district network operator for this particular region up here. DNOs are prepared for heat pumps. They know they're coming, they know they're coming at scale, and they're actually viewing the controllable load and the ability to load shift with an electrified heating system like a heat pump as potentially benefits of grid management. They're a little bit more concerned about lots of direct electric heaters, though. That's a different story. But the way that the heat pumps operate, they're prepared, and these things are being factored in. Frazzling the grid isn't really on the cards. Now, as for some heat pump truths, though, you will need a cylinder for domestic hot water, and you'll probably need a buffer cylinder as well of some description. Not really, I suppose, an unexpected given how heat pumps operate. But again, it's always worth highlighting that, yes, you will need to find space for a domestic hot water cylinder. The majority of properties used to have one in the olden days. So, it's not inconceivable that we can find a space for it, but be prepared, you will need one. Source, they do need external space as well. So you've got the box on the outside of your property. Split systems and monoblocks, there's pros and cons of both. Some can be sited further away from your property, like at the bottom of the garden or what have you, but you still need to find space for that box on the outside of the house. A heat pump may require planning permission. Now, although the majority of installs comply with permitted development, there are some circumstances where you will probably have to apply for planning. So again, be prepared for that. These aren't we can't say you can just install these things. There may be requirements for planning permission. And the last point, again, Nathan's reiterated this already, it's not a boiler. Boilers design seat up from scratch. Heat pumps top up the heat. Rather than filling that bucket from empty, with the tap on full, the heat pump drips the water back into that bucket to maintain that it's always full. If you use it like a boiler, if you switch it off and on, it's going to cost you a fortune in running costs, but equally in replacement parts, because as we know, as we've already found out, they don't like being switched on and off. That's not how they're supposed to operate. So hopefully that's addressed some things that, well, you are aware of now anyway, because Nathan's gone through it. But again, just to reiterate that these points, there are some truths and some myths around heat pumps. So what about the role of heat pumps in zero carbon housing? Well, the first one, I think, and this is something that lots of landlords and local authorities have come to accept, we can't afford to wait to address the carbon issue. So 2050 for the UK, 2038 for Greater Manchester. These dates for carbon neutrality were identified and set and based with a carbon budget in mind. That's to say there's this much carbon that we can emit between now and that end date. That gives us the middle line, the linear trajectory for carbon reduction. Every day that we're not reducing our carbon emissions in line with that linear line, we are adding to our carbon budget. We're putting more carbon into our atmosphere that we will have to offset at a later date. If we did nothing in Greater Manchester until the 31st of December 2037, and then overnight, we'd achieved carbon neutrality, we'll still fry. We will have still blown our carbon budget. The area under the graph not the line, not the trajectory of reduction. It's the area under the graph that's important, because that represents how much carbon we've got to play with. We don't reduce carbon, yeah, we've just got more to do in a shorter space of time later on, which means ruling out waiting for hydrogen. Electricity Northwest and Cadent have done a lot of research on this particular issue, and they've produced a number of very good reports, decarbonisation pathways for the Northwest. Even in the Northwest, which has got a rapidly developing hydrogen cluster over in the Ellesmere Portway in Merseyside, the powers that be, those organisations that manage our energy networks locally, recognise that there ain't going to be anything like a meaningful quantity of hydrogen in the domestic network this side of 2035. So from a social housing perspective, you can install a hydrogen-ready boiler thinking you're doing the right thing, but actually take it out before it's burnt any hydrogen when it comes to replace the thing in 12, 13, 14 years' time. Install a H2-ready boiler now and save no carbon now either. It's unfortunate, but that's where we are. We will need hydrogen, and there will be problem nuts that the hydrogen hammer can crack, but realistically speaking, right now we can't wait. We can't install hydrogen burning appliances on the off chance that some hydrogen might come down the pipes in the next 15 years. Whereas we do know that the grid is decarbonising, and it's decarbonising at pace. So you've got the government's 10-point plan, the energy white paper, that all these investments in offshore renewables and onshore renewables as well. Grid decarbonisation can be relied upon rather than hoped for, I think, and that is something that is being recognised more widely across the landlords that we work with, and equally the local authorities. But what does this actually mean in relation to how landlords are going to address zero carbon in their stock? Well, some research that's been produced for the Greater Manchester Combined Authority, it's not yet published, but it will be in the not too distant. It confirms a few things that should be bleeding obvious. Fossil fuels have no place in net zero carbon housing. We've just got to tackle burning of gas effectively. Heat pumps and PV play a key role, and if you're summarising it, even further, dumbing it proper down, the heat pump is required to address the carbon emissions from the stock, and the PV there is required to address perceptions, at least, of fuel bill costs. PV generates a cashable saving for the tenant, which offsets perceived increases in running costs from electrified heating systems. Equally, the grid decarbonisation needs to be factored into these things, and the day one carbon savings. The day one bill savings increase over time. These things are useful in terms of freeing up a little bit of extra resource with which we can do some fabric works. Fabric improvements are still required, but broadly speaking, and again, this was something that was quite interesting that came out of this latest research. If you went berserk on the fabric and put a new gas boiler in there, you would still have a higher carbon emitting property than an energy performance certificate rating of a C with a heat pump and PV on. So not groundbreaking levels of fabric improvement. It's the fuel, it's the heat source that's the real issue in relation to carbon emissions from housing. So I'll just touch on a couple of the projects that we've been involved in that focus on air source deployment before touching on equally some of the lessons that have come from these projects. So we've got the NEDO project, or give it its full title, the Greater Manchester Smart Community Demonstration Project. So this was part funded by the Japanese government, and that saw around about 650 air source heat pumps installed across Greater Manchester. So Wigan, Bury and Manchester as well. So these targeted gas and electrically heated homes. There was a mixture of hybrids, splits and monoblocks. And it was to demonstrate the viability of heat pump deployment at scale and effectively how much electricity could be saved by switching these things off all at once. How can we address peak demand? So it's the first demand side response trial of its kind. Very, very successful. It demonstrated you could save loads of electricity by switching a heat pump off, but again, it's an electrified heating system. That shouldn't come as any great surprise. But the overwhelming response from the people that had these things installed was wonderful. It was giving them control. It was saving them money on their fuel bills, and they were very, very happy with this new heat system. Your housing group, they removed their entire stock in one Staffordshire village in Longner, just outside of Leek. It's an off-gas village. They had serious problems with oil combi boilers and things like that. They went down the heat pump route because they identified that it gave the tenants a lower cost heat solution, but equally it reduced maintenance cost. There was a whole host of other reasons why that landlord wanted to go down that particular route, but that was not a massive number of heat pumps itself, but it was quite marked insofar as it was all of their stock in this village. They moved away from oil to heat pumps, relatively speaking, overnight. The Homes as Energy Systems project, and that's something that we're involved in. That's ERDF funded. It's more than source. It's 250 plus source in Stockport and Manchester. There's another 500 odd ground source going in as well, and that's targeting gas, communal gas properties, as well as electrically heated properties. So the whole range of things. And the primary reason for this particular project is to build on NEDA. So going beyond how much electricity can we save by switching these things off, it's how much electricity and carbon can we save by switching these things off and on. What happens if we do this when there's a spike in demand in the grid? What happens when we do that when the grid frequency drops below its normal operating parameters? What can we do to generate revenue? How do we offer grid management services to district network operators and to National Grid? It's looking at all of these kinds of things. Right now, we're on with a whole host of local authority delivery scheme funded works, Green Homes Grant, LADS projects with Wigan Council, Bolton at Home, Together Housing Group, Carbon Homes. Again, 200 plus air source going in, primarily targeted at E, F and G rated properties. And again, a mixture of gas and electrically heated ones as well. Just to underline that, it doesn't have to go in an energy efficient property for it to work properly. And another very, very challenging and innovative project is with Southway Housing Trust in Manchester, and they are switching an entire estate over to air source from gas. So this is individual combi systems and small communal heated systems. It's 400 properties, near Manchester South Cemetery. It's given Electricity North West quite a bit of an headache because it's a lot of juice going into not a lot of space. But I'll touch on that in a second. It demonstrates the appetite and the range of things that landlords are looking at. In relation to learning, how do we make these things work a little bit smoother? Well, first off, with your project, engage with planners. So I mentioned permitted development, and you may require planning. This is certainly an instance where planning has been required. And this is where we're looking at deploying air source on low-rise flats. So the bottom of my wonderfully drawn up diagram there is effectively it's to demonstrate a set of flats, a cottage flat, a walk-up, a maisonette, whatever you want to call them. Two flats in a pair of semis. The picture above two semis, you can achieve permitted development. You can achieve installation on a building that looks just like that. However, the minute you have two heat pumps on the curtilage of one dwelling, you've got to go through planning. And ostensibly from the outside, the buildings look just like a pair of semis, but from a planning perspective, they have to be treated differently. For our landlords that have got lots and lots and lots of walk-up flats or cottage flats, the scope for swamping the local planning authority is quite real. And one scheme, the Homes as Energy Systems project specifically, has demonstrated capacity issues within local planning authorities precisely because of this kind of property. Equally, engage with your environmental health teams, because if you've got to go through planning, you might have an issue with air source. So this is not particular, it's not unique to Manchester, but Manchester's environmental health officers have got specific nighttime noise restrictions from plant associated with heating and all that kind of stuff if planning is required. So in a nutshell, Manchester City require nighttime noise levels to be 5 decibels lower than background noise. Background noise on average in and around these areas of Manchester where these things are going is 30 decibels, which means you need 25 dB at night. 25 dB is an empty recording studio, and that was a quote from an acoustic engineer. Even with noise reduction kits, a lot of the air source units currently are louder than that requirement. interestingly enough, a domestic boiler flue is louder than that requirement, but the domestic boiler flue doesn't require planning, and therefore it can go in easy peasy. Likewise, the air source that are permitted development don't require planning and can be installed. But any kind of project that involves planning for installation of an air source, plan ahead, for want of a better phrase. Equally engage with the DNO. So the majority of individual installations, you would specify connect and notify air source heat pump unit, which means you can connect the thing and then notify the district network operator. However, if you're installing at scale, you still need to go through an application process. Understanding the properties that you're looking at installing these things onto is useful, because again, you would have to notify the DNO if a property's got a looped electricity supply. That takes time. The DNO won't frustrate you. They will undertake that conversion, but it adds time to the process. But yeah, if you're looking at multiple installs like we're doing, you've really got to get into the guts of the DNO, because they require information from you as a customer that you aren't able to provide them when they need it. So a landlord might want to get an understanding of, broadly speaking, is this viable? The DNO could not give an indication if it's broadly viable without understanding exactly how many heat pumps, exactly what make, model, capacity, exactly where these things are going. DNOs and landlord processes aren't aligned, but they are starting to get there, which is nice. And of course, we've got to engage with the tenant. So to secure, I suppose, resident sign up and all this kind of stuff, there are some key messages that you need to get across, and there's a lot of work that you need to undertake as well. So reinforcing, you will need a domestic hot water cylinder. There will be internal space impacts. You're going to lose your cylinder, the airing cupboard that you thought you'd won when we took out your system boiler. Likewise, best to assume that a buffer is going to go in there as well. So you need a little bit of additional space. All-in-one, pre-plumbed domestic hot water cylinders and buffer units in one, they start to help address these things, but still, you will lose a bit of space inside. Handover is critical. You need to explain how they work and how they need to be used. So again, warm, not hot radiators on for a longer period of time. Touch it, it's not going to take your skin off. The thing's still working. Don't fret, Mrs. or Mr. Smith. Likewise, explaining the impact on bills is useful. And this is something that came out of NEDO. People were very, very upset that their electricity bill had gone up. It's gone through the roof. Well, it has, because you're now electrically heating your property rather than gas. What's your gas bill? Well, it's gone. Oh, simple things like that. Explaining how one might increase, but one will decrease, and all that kind of stuff helps to avoid confusion. Likewise, renewing or reviewing energy tariffs is relatively essential also. If you were on economy 7, well, get off that sharpish. Because if this thing is operating 24/7 effectively, you will be penalised if you don't explore and understand what is the best the best electricity tariff for you. Time of use things coming in, I'm not sure what role they will have in relation to the social housing tenant, but there are opportunities for certainly for owner occupiers with energy storage and larger buffer cylinders to really do some weird and wonderful things with the heat pump to generate bill savings through load shifting. Penultimate slide, you'll be pleased to know the future plans for heat pump deployment. Well, in the social housing sector, I think deployment at scale is inevitable. Landlords are looking to reduce carbon emissions. They're looking to reduce the costs of managing gas, the gas risk within their stock, and they're looking at supporting residents with fuel bill reduction as well. So equally, smart monitoring and smart control gives the landlord that assurance that the system is working as it should. They're looking at deploying PV, whether they need to or not to reduce, to provide a fuel bill saving to a tenant is arguable, but they're looking at deploying PV with air source at the same time anyway to provide running cost reductions regardless. They're looking at other ways of using heat pumps and controllable load to generate revenue through grid management services and such like. And ultimately, we've already started to see it. Costs will reduce with deployment. So the little graph on the right was the cost of PV per kilowatt peak installed over 20, 30 years. Swanson's law dictates with every increase in capacity or what have you, costs reduce exponentially. And that will happen with deployment of heat pumps also. Last thing to mention on here is, in light of all this continued or increased demand, we're going to market imminently for it's a new low and zero carbon technologies framework, and that will cover both the supply as well as the installation of air source technologies, ground source, PV and batteries, and heat interface units for communal heating systems. So Andy's stuff, who you'll hear up next, and equally Gemma's stuff from Vital, which is another presentation later on. That was me. I think I just kept it to 25. Apologies, but there we go. I shall end my slideshow, I hope. There we go.
Great, thank you very much for that, Dave. We have got a few questions in. Salma did ask, what about fabric first? Should we not insulate first? Now, I think you covered a bit of it, and I've said fabric first is a given. But, you know, certainly my work with historic buildings, I know that you can't always take the fabric into account. And I'm sure, are those leaded lights, is that single glazed or double glazed units behind you?
This is double, sir. It's double. So fabric first is a laudable principle, but it's not a dogma. I think we can demonstrate that these systems work effectively in properties with an energy performance certificate rating of C without any significant detriment to their performance, as long as you can design the heat emitters correctly, and all of that kind of stuff. The research that came out of Great Manchester Combined Authority, again, it demonstrated that heat pumps as the next solution were cost-effective fabric measures have been done. So if you've got cavities, they should be filled. If you've got a loft, crikey, don't be sat here not insulating your loft if you haven't got 270 mil of loft roll in there. Go on and do that now. So there are sensible things to be done, but you don't need passive house levels of performance for a heat pump to work, and that's been proven time and time again. But fabric is important. It's a principle, but not a dogma.
Got another question here from Matthew, touching on these sort of tariffs in economy 7. It was saying that, for example, if you had an economy 7 tariff and it was driving you maybe with some algorithm to use the heat pump more of a night, wouldn't that conflict with the noise reduction issues that you're talking about, the acoustics?
Yeah, it would, to be fair. So there are quite a few contradictions in all of this stuff. You're right. It's more this concept of, I suppose, the load shift, the ability to store a large body of hot water. So if you did have a big old buffer cylinder, and that's not really something that would be applicable to the social housing sector, I don't think, because of space issues, or a heat battery. If Octopus on their Octopus Agile tariff were paying you to use electricity at 3 o'clock in the morning, crikey, you'd fill your battery or you'd fill your heat store. But yes, there are trade-offs with this one, and Manchester City Council probably wouldn't let you anyway if you had to go for planning for it. So that point around energy tariffs was more about those socially rented or socially tenanted properties that were previously on an electric storage heater, and they charge the thing up overnight. If they do not move away from that, they will be stung financially, because they will start, the heating system isn't just charging at night. So that's what that point was more about.
Okay, got another question from Kelvin, which I'll answer directly. He's asking about the videos and slides. Yes, we'll make these available. They will be published and put online, and we'll email everyone. It may take a couple of weeks in order to do that. I've got a couple of questions for you, Dave, as you expect I might. Well, one's first is that I know with regard to noise, that our acoustics team, we've got an acoustic lab at the university, and Bays are engaging with us at the moment to look at the noise issues with surrounding air source heat pumps. So that's something optimistic. With regard to the DNO and the loading, is it just the amount of load on there, or is it to do with the harmonics as well?
Well, it's a bit of both. So when we were going through Hayes, initially it was a case of, the Homes Energy Systems project. We identified the areas where these heat pumps will be going in. Can you undertake a high level assessment? And this is the first time of its kind, I think, that the DNO had been asked to look at something like this. And broadly speaking, that should be fine. But when we started getting into it, the level of information that they required, it was very, very granular. They wanted to know exactly which heat pumps were going to go in. They wanted to know exactly what size. They wanted to know, what model, whether they complied with this and the other. And at this particular stage, the procurement of the kit hadn't actually happened, so we couldn't tell them with any kind of certainty, well, it's going to be a NEBA F1255 or a Kenza shoebox or a Panasonic, whatever it is, which meant that they weren't able to do the detailed modelling that they felt they had to do to be able to give us a ballpark answer. They wanted stuff we couldn't give them, and without us giving them the information that we hadn't got, they weren't able to provide us with assurance that it wasn't going to be an issue going forward, and we just went round and round in circles. It's more to do, harmonics is an issue, but the primary concern when we were engaging with the DNO was peak demand. And again, the way that they looked at the heat pumps, in one instance it was 70 going in one tower block, 70 units, and crudely speaking it was, on each one of these has got 33 amp load in it. Crikey, if they all went on at exactly the same time, it's going to pop stuff. Well, that will never happen. For starters, we can build this diversity in, and there are a number of different reasons why that wouldn't happen, but they're obliged. And again, this is primarily from the Electricity Network Association, not their own, imaginings. They are obliged to model, the worst case scenario, even if the worst case scenario wasn't actually going to, if it physically couldn't happen. They still had to look at it and pretend it would. But harmonics and peak demand, were the things that they had to assess, and they have subsequently had to upgrade a couple of substations.
Great, that's really good. Yeah, I think the substation thing is quite interesting as well, because I've worked on a couple of projects in East Anglia with the National Trust where we needed substation upgrades as well, and that takes time.
It can, and that's one of the challenges that the Arrowfield Estate project is currently looking at. There's 3 million quid's worth of substation upgrades being programmed in. ERDF is the funder for that one, and money needs to be spent within a particular time frame. So the project is ultimately now beholden to ENWL's investment program. But because of the lessons that was learnt on, or were the lessons that were learnt on Holmes' energy systems, it's a slightly different process being followed now by the DNO and our Southway Housing Trust on that particular project. So things are moving forward quite nicely.
Great. Well, if there is no more questions, I think we will move to the break. I'm certainly going to have a discussion in the break with Dave about the idea of fine wines from Bickershaw Colliery in Wigan. That's
wonderful
terroir. Interesting to me. Yes. But yes, the cover break's coming up. You go away, get yourself a drink, or you can. We will set up some breakout rooms where you can go into and meet up with your fellow participants. So if you could switch to that, that'd be great. Thank you. Oh, we will be back at just after 2:30. So we're about 15 minutes ahead of time. Thank you. Welcome back, everybody. Here we are for the next session. We've got Andy on ground source heat pumps, and then Gemma and Glenn doing a double header on heat networks, followed unfortunately by myself. I'm doing a little bit on the remaining low carbon heat technologies. But what we'll do, we'll move straight on to Andy. Andy initially began work on the drilling side of things before becoming immersed in all aspects of design and installation. Since then, he is dedicated to providing expert provision of renewable solutions to domestic and commercial clients and architects, as well as involving himself heavily in industrial education and regulation. And he works with the Ground Source Heat Pump Association and is on their council. So I've worked with Andy for quite a while. He certainly knows his
see next
stuff.
slide.
I'll
We'll get
leave
to
it
next
to you,
slide.
Andy. Take away.
No. How do I go? Thank you. Where is me? Am I on?
You're on.
You're on, Andy.
I'm on. So, yeah, as you know, old age and technical ability with all this new stuff. Can everybody see everything? I hope you.
We can see your screen, your presentation. We can't see you, but it's up to you whether you want to have your camera on or not.
I'll put the camera on at the end. Maybe it's a good thing not to see me. But yeah, I'm more than happy to put my camera on at the end. So this is a bit more of a practical approach. More than anything, I've been involved in ground source heat pumps, like I say, for the last 22 years. All at the start was all about design and installation to make sure that obviously this stuff is installed correctly. But as we all know, as we get a bit further on to it, building physics comes into it a little bit more. And I'm going to have a brief chat about the way that we design the ground loops and the future way to design ground loops. At this minute, it's not based on fact. You can't apply physics to an assumption. So I'll digress into the future. So at this moment, as you can see, this is who we are. This is what we do. We're a family-run business, as you can see. We cover all aspects of design, but there's a sort of like key elements that run along now with new builds where air sources heat pumps are into it. We've done solar thermal just as long as we've done ground source. Now we've got mechanical ventilation heat recovery coming in, especially now we get more air tightness is better, and SAP plays a large part of that. And typically, you know, underfloor heating at any stage that we can, especially on the new builds. And then if you want to, we can do rainwater harvesting, but at this moment in time, I'm very sure that you know that we don't really need to do a great deal of that. Okay, on to the next slide. Okay, guys, this isn't a new technology. I'd like to think it was, and we were turning the earth with this and making progress, but unfortunately, we made the fridge before we made the heat pump. And Lord Kelvin in 1852 was one of the underlying factors for heat pumps. But as you can see, our first patented heat pump was in 1912, which was Heinrich Zolle. And it's gone on from there, shall we say. Heat pumps have evolved, technology's evolved, the actual electrical systems haven't evolved. Shall we say that we've still got a dirty grid. So the grid people still need to pull the finger out and get that sorted sooner than later. As you can see, in 2004, we only had 150 ground source heat pumps installed. Just to let you know, in Ireland, I was installing 100 a year in Ireland. So we're a bit late stage here, but their government had some really good ways of making people buy them. I'm going to run you briefly through the technology. I'm sure some of you may be sick to death of seeing the same sort of slide. But yet again, as you can see, it's a compressor cycle, obviously. And basically a lot of it's based on how we can do the thermal transfer from the ground. What we're relying on from the ground is our temperatures at fixed temperature if possible. And yet again, guys, that's all down to design. And we'll have to talk our best way through that at this moment in time with what we've got. So we've got high temperatures, which is suitable for heating purpose. And this occurs through a closed cycle, which processes the fluid and consistently undergoing changes. When we call that, obviously, that state of change with what we call adiabatic energy. If you worked in applied thermodynamics, you'd understand that. But we don't need to be that sort of way. That's already going on in the heat pump. The heat pump's doing it for you, just like your fridge does for you, really, to be fair. And we don't need to do applied thermodynamics to understand that neither. But what we are looking at is inlet temperatures. Inlet temperatures are quite a key thing to make sure that we've got a 3.6 to 4 or maybe higher, depending on what part of the world we're in, what part of the country we're in. It was quite interesting. I was listening to a discussion before, a chap called Ken Gordon, and yes, quite rightly so. I have started recording ground temperatures up and down this country, because everything's based on, is it a rule of thumb? And at this moment, it's rule of thumb. We need to take that and make the physics into facts. So our next market that we look at, which is sectors of domestic and commercial. And these are the two sort of areas that, you know, heat pumps, ground source, you know, work very well in. You know, we could be providing heating for a pool, even on a domestic. We could be providing heating for multiples on the commercial, but we need to make sure that we size that ground array correctly to suit the longevity of the system. So going back onto heat pumps in the UK, I just wanted to cover this because, as you can see, this isn't great. I'm sorry about this. It's the light green is the air source heat pumps, and the dark green is the ground. And if you look there, we've been pretty static on our sales sort of end of it all. I mean, in the early days, we used to do quite a bit of solar thermal, as you can quite see in 2011, but as PVs come along and we've got the Emerson and the iBoost and other technologies that can boost the immersion heater, we can see that obviously at that point there is that's where it starts to take a drop. I quite like the idea of solar thermal. We can use that in a ground loop basis. We can use that to lift temperature, even in the winter months. I wouldn't say that we'd use a ground as a thermal dump, because that is not the way to use a ground loop. But it is good for keeping the heat pump very low running, kilowatt running hours through them summer months anyway, at least for 8 months of the year, to be fair, doing hot water demand. So it's at this stage now I want to talk about different applications for ground source heat pumps, and there is numerous ways to do these systems, and I've seen some very wrong ones, but we can talk about that after. I'll move on to the next slide. So when we're talking about this consists of obviously more than one vertical hole, depth ranged at least between 80 to 200 meters. Drillers start to run into problems really, depending on obviously what we call the ground is what we call the aluminosilicate. That silicate is different stratas. Typically, as you'll get up into Scotland, you'll get to more granite. Obviously, as we get further down in the south, we'll hit a little bit more chalk and flint. You know, we'll go through boulderstone clay, or as we get up near here in north, shall we say, Manchester, we'll hit a bit more blink fire rock, which is coal measures. So obviously understanding what the watts per meter Kelvin are from there is something that needs to be looked at on a design person. So as that person, as you give them that geology in that area, which they're going to look at, that's the sort of thing you're looking at. I will say, as you get more loops in the ground, you need to make sure that you've got your pumping effort correctly done. Pumping effort and pressure losses are key elements to make sure that, or else otherwise you'll pull off one borehole, then you will pull off another borehole. So you need to make sure that's got done right. Okay, a couple of practical pictures, which I suppose a lot of you have seen. On the left-hand side, it was a very cold day that day. You can see a drilling rig, and on the left-hand side here, if you can see where my arrow is, you can see a decoiler for decoiling the ground loops. And then in the middle, you've got two tails sticking out, and obviously they need to, what you can see around the top there actually is what we call the grouts. And that grout, the specification for that grout and the standards is it needs to have at least a conductivity of 1.73 watts per meter Kelvin, which if it was a perfect borehole, yeah, but if it's an aquifer at any sort of point, then you can forget the watts per meter Kelvin. That grout will not do what it's intended to do. But it's the best thing that we can do at this moment, and obviously it does support it as a bit of a pile if it's near any building, so at least you've got some structural values. And then on the right, what you're looking at is there is actually 5 boreholes on that picture. The one's on the left, you can't really see it quite well. But what we've got there is obviously a chamber, which is the white unit in the middle. On the left-hand side is a fusion welder with obviously a little generator, and we've headed off and we are waiting to do the header works into the building, which is the two little bottom pipe works there. Sizing header works is quite a key attribution to the system as well. You know, you can't put that amount of fluid down the 40mm pipe work. You know, you need to size your pipe works on your distance from the chamber to the house, and then on the flow rate that you're providing. It might be 8 meters ahead, 12 meters ahead. It all depends on what you've got going on. So on to the next slide. This is a horizontal array. You know, they are sort of like the easier version to do, shall we say, but you're going to need, you know, I won't say a large field, but you're going to need a good area that's going to be sustainable for your house. Now, ground source heat pumps, peak demand, we could say, okay, we've got a peak demand of 20 kilowatts. But what we might have is a long kilowatt running hours of the system. So we need to make sure that the ground array is based on the kilowatt running hours, not the peak demand. Because the peak demand could be, you could have a swimming pool in the house. So your peak demand might be only 5 kilowatts more, but you may be running another, say another 15,000 kilowatt hours longer. So that system would run longer. Obviously, as we all well know, the longer you run a system, the more energy it needs. And if you've not got enough the right amount of energy in the ground, you will burn through that ground loop quicker than anything. So I'm going to move on to the next picture. This is an horizontal, this is a typical array that you can see yet again, chamber on the left-hand side, ground source heat pump with a buffer tank in the middle. I couldn't get the cylinder on because it's at the back of me. And we have got 6 trenches, and them trenches are 150 meters each, so 300 meters in each coil. Okay, moving on to open loop systems. Now, what I'll say about open loop systems is that they are high maintenance. Normally, open loop systems normally pretty good for doing commercial buildings where you've got a sort of service manager guy in charge and can either backflush the system or clean out the filters on the system, but you need to make sure the quality of the water is good. So firstly, it's best to get a hydrologist and a geologist involved if you want to do open loop. They'll need to measure the aquifer flow to make sure what directions it's going in, and obviously that you're not taking it off your local brewery down the road or something like that. But you need to obtain environmental, the EA agency, to make sure that you've got an abstraction license and also a re-injection that you're putting it into the right place. Lab samples, yet again, will be taken for quality to indicate discharge methods, and flow will be needed to be checked periodically to obviously to understand in the summer months that doesn't dry up or you don't dry somebody else up. Obviously, making sure that the driller follows the methods of the drilling standards, which you'll find on the GSHPA website sort of thing, is another thing to be checked. These guys need to make sure that they're following that standard, or else I'll show you another picture in a bit. You could be in a world of hurt. Okay, shared ground loop systems came about through really the RHI. But yet again, shared ground loops was done, a lot of it was done in Norway, Sweden, and yeah, it saves on area that you're going to do your multiple drillings, as in where you can do single aerated drillings. I'm going to move on to the next slide, guys, because that is sort of like a typical shared ground loop. So we've got a house in the top left-hand corner, and we've got another house in the right-hand corner, as you can see, and they're sharing a loop. Now, if you had sort of 2 houses here, then, you know, you just need one singularity borehole. Yet again, that borehole wants to be based on the kilowatt running hours of both systems. And that's not to say that, you know, one guy or one house may be empty for 6 months and he might work away, but you've got to understand that can always be the same all the way through it. It's got to be done. no, we can say we use FLEC running hours, which might be 2,600 FLEC running hours on these ground arrays, but the ground's based on kilowatt running hours, and the peak demand is based on the size of the heat pump, based on how much hot water and heating you're going to be supplied. From my sort of aspect of it, when I'm doing a design, I look at the reheat time of the hot water cylinder. Obviously, I'm looking at, based on what the SAP reports or the heat loss calculation of the building is. And then based on that, that's how we're going to sort of size our heat pump and understand how soon we can reheat that house. Okay, next one. Same again. This is for heating and cooling. I used to do a lot of this in Canada. Not need a great deal for it in this country, except for some places, a couple of museums that I've done where temperatures need to be done at a constant temperature. Very self-explanatory. You know, in the cold weather on the left, you know, we're using the ground for heating because obviously it's a lot more warmer than it is, and we're using the compression cycle for doing that. And then on the right-hand side, we're using the ground temperature to give us a passive cooling. It's not cooling like you said it would, but when I was in Canada and it was above 40 degrees, it felt pretty cool. In fact, actually, some of the problems we had in Canada was that the ground temperature would cut out the heat pump because we would be abstracting too much energy from above and putting it in the ground, and we couldn't disperse it quick enough in the groundwork. So the temperature became too warm in the ground, the heat pump won't run. So I'm going to move on to another technology, which is on the left-hand side here. Looks like an air source heat pump. Theoretically, you could say it is, but it is what we call a dry air cooler. And the idea behind a dry air cooler is normally used in European countries like Spain, etc. But yet again, we started doing them here in the UK, where it saves on the amount of gram loop that's required. So that in the summer months, obviously, once you get above 10 degrees, you want to be able to use your dry air cooler. And I won't say you make your gram loop redundant, but as it gets warmer, you will start to use the more heat from that dry air cooler, and it makes the heat pump more efficient to produce hot water. And then obviously, as it gets to 5 degrees, etc., your ground array becomes more useful, and then you'll use your gram loop more than you would your passive, your dry air cooler. Going on to the next one. I'm sorry if this is a bit death by PowerPoint, guys, but it's not very often I do PowerPoint. So let's talk about technologies. And smart technologies is quite a key thing now. Yet again, David Kemp was saying before about how we deal with agile tariffs. Well, some of the heat pumps now, obviously, and well, pretty much the majority of heat pumps are inverter driven, and pretty much most of them are running with software systems in there to be able to see on and off peak tariffs. You know, if you're going to make a cup of tea when Coronation Street's on, or whatever else you watch at the 7 o'clock time of night, it's going to be a bit more expensive than it would be at, shall we say, 2 o'clock in the morning. So it's quite a key area to make sure that these heat pumps can see that when we require the demand. And there's systems out there now are doing a lot of remote sort of talking to what the incoming peak tariff is, what the off-peak tariff is, how we can work alongside with what your battery storage is, what your PV is running at. Even if you come home and plug your 17 kilowatt battery off your car into your house, and you wanted to use that, then use, your normal domestic incoming supply. So these heat pumps, yeah, we can fine tune these. You can't fine tune gas. And we're getting to a good stage. It's just that the grid is a bit dirty, and it's been dirty for some time, the electric grid. Won't move on because I can talk too much. Sorry, guys. So this is your bit. Design, 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 design. I do believe we can get building physics right. And we are getting to a good stage where we have understanding of better fabrics. So 20 years ago, we weren't really looking at building fabrics. We was just looking at, this is a heat pump, it's going to be a bit better technology than gas. So, but now building fabrics is quite a key element. So we need to make sure that we're compliant with building reg standards. We need to complete a full room by room heat loss calcs. And let's not make the nudge figure too much on the heat loss calc. Let's be realistic. Consider the exposure that you're at. In other words, you know, are you up in the islands of Scotland, or are you down in the south in Hampshire or Kent where it's that slightly bit warmer? Yeah, again, obvious, choose high quality building materials. Application to your DNO is quite a key thing. It's one of the first things that we sort of get out of the way first. These guys can stop your project before you start, or your client's going to pay a bit more money to make sure that they've got the network up to standard in their area. Yeah, planning. If the building's listed or if you're conservation area, just check out your permitted development. Analyze the ground strata, because that ground strata is quite a key thing for the thermal conductivity. Unfortunately, at this moment, we've got the BGS reports, but I am running, as I said before, I am running tests on the ground. I've got some software and hardware where I'm putting them in on ground loops, and I'm getting readings from external temperatures of the ground loops to the internal temperatures of ground loops, which is quite a key matter. We need to see what's going on in the ground. Site inspections are quite key to make sure that your clients, you know, got a good inspection done, and risk assessments and boreholes. So then you know, your driller just don't turn up to site, and next minute you can't even get down the driveway. I've seen that before. Utilities, make sure you're not going to go through electric and water and gas. Some regions require coal authority checks, which is quite a key thing in the area. Plant room design, most definitely key. Making sure that you've got these systems in the right place, making sure that some of the older days where the heat pump isn't next door to somebody's office and it isn't buzzing away. And external header pipes and chainworks locations are quite key too. So I just want to go to make sure I quite feel that the key sort of thing is understanding ground loops. And what you're looking at here is what we call a dry bulb. And our ground works at least 3 months behind what we've already got going on now. And at this moment in time, it's doing heating season at this moment in time. Obviously, as we do less heating, that dry bulb will start to relax. And because the ground was never mined for energy before, but now we're mining for energy. All right, coal's a different thing. You know, we took it out, but at this point, we're abstracting heat. But we're basing our heat based on what BGS tell us what's in that area, which isn't necessarily correct. I've done many jobs where what we call fissures that run through the system. They say that I'm in salt, and actually, no, I'm not. I'm in bullstone clay, which is a different watts per meter Kelvin altogether. So at this moment in time, we just need to go off what we've got and base our best temperatures, but not adding too much of a fudge figure on top is quite a key element. So next slide. As I mentioned before, making sure we've got good heat loss calcs. Calculating peak loads, heat and hot water demands, quite a key area. Design outside temperatures based on different regions, like I mentioned before. Building location for exposure. You know, I know Dave has been involved in blocks of flats and stuff. Yeah, again, these guys are exposed when you get on the 10th floor, you know, and you're going to get positive and negative pressures playing a large amount in it once that wind starts ripping up around it. Building fabric, as we all well know, is a key element. Property builds year, you know, we need to make sure that that builds year of that property. You know, can we upgrade this property to make sure we've got 25 mil or even on the walls plasterboarded? Design room temperatures to make sure that we're actually being realistic. Air change factors, especially on new builds, air change factors, you know, we get MVHR into these systems now. And if we can lift the air changes from your standard 1.5, 1.3, and we can move them up to the 8s and the 10s, we'll get more air changes. It's better to move air around. Heating elements and deflight, you know, your flow temperatures are quite a key thing to make sure you can get your design flow temperatures. On the right hand side there, where you can see the estimated load profile, that is sort of like your dry bulb situation, where we know that sort of May now, we should be warming up a bit, although we've had the driest April roundabout, but we should be looking at moving to summer, and this is where the ground should start to relax, and that peak kilowatt running hours will start to, you know, relax itself. Okay, so these are just typical plant rooms, but your typical size of a plant room, you know, you can do combination buffers and cylinders in smaller properties. And also you can do, so, you know, we look at, so we say 2 meters to 2.5 in length and at least a meter in depth. The one in the middle at the bottom is a 2,000 litre buffer tank, which is supplying 3 properties down in South Wales. And pretty much most of these other ones are just serving large commercial buildings. Some of the large houses, you know, 35 kilowatts, 45 kilowatts, going into, well, 100 kilowatts these days. Yeah, again, I'm just sort of giving you an overlook, brief overlook of what you're looking at when you're having a heat pump fitted. So, poor design, unhappy clients, the last thing you want, it is your bullet in the gun that's ready to get loaded. So, some of the systems will go out to instant headache. So, on the left at the top, you can quite clearly see that this is in October. This system's been in 6 months. There's 3 ice pops there that are just starting to form. And then if you look around the edge of the chamber, the water's just starting to freeze. And that is because, firstly, the ground loops into much of a small area. So the guys have put slinkies in, and we've got, so if you're trying to pull an average 30 watts a square meter, but now you're actually pulling 50 watts a square meter because you've got more pipe work in there, you're going to have an headache. Middle picture, the chamber I went out to, and that chamber was leaking, and it had ethylene glycol in, which we don't use anymore, and it had started to kill pretty much all the trees around that area. The second one, the third one on the bottom left there, I'm just showing a soft start, which I kept blowing. That's because the compressor kept coming in and out all the time because it kept duty cycling. And it was duty cycling because the heating system wasn't set up correctly. The other one on the right there with the round circle around it is an immersion heater, an inline immersion heater that has started to burn out because it was consistently on. And the other one is an energy fence, which is a sort of German invention. It might work great in Germany, but it's not doing a great much for us in our country. So we're saying other examples of poor design. So on your left-hand side and on your right-hand side are what we call artesian wells. So I would say, if you're going to do open loop, guys, make sure you've got a geologist involved or a hydrologist, because if you hit an artesian well, get your wellies on quick. The other one is contaminated ground loop. Another system went out to. And then we had, in the next one to it there, is a leaking manifold chamber, which in the midst of winter isn't great because that was full and it was frozen solid. And I had to wait 2 months before I could go back and sort out the leaking chamber at the bottom. Okay, so there are standards for the UK, vertical borehole standards, thermal pile standards, shallow ground source standard, etc. So the standards are there. They're, you know, more than anything, we need to have some sort of standard to go by. I won't say that it is biblical, but there needs to be some sort of standard. And you'll find these on the GSHPA sort of website if you want to go look at them. And I'm pretty much done, guys. Like I say, I'm a bit more of a practical guy. I do design, but the reality check is that you can easily get this wrong. It's not a rocket science, and you don't need to be a scientist. But just applying yourself to the right method will solve any problem you've got. And I'm sorry, I've run on a bit, but okay. Sorry, Nigel, I'll cut myself off.
No problem at all, Andy. That was great, as per usual. Can we see you now as well? Can you put your video on?
Oh,
so
yeah, we can do all that.
Yeah, and then we'll run through a few questions there. So we have got quite a few questions in here. Let's have a look. So first question in from Stuart. How adaptable is an installation if future developments are planned?
Sorry, just 1 minute, Nigel. I'm just doing something, mate. I'm just trying to put you over here. Can pick it up. Right. Just put you on the other screen. Sorry, just repeat that, mate. Sorry about that.
Yeah, so if you put a system in and I guess if you want to expand it, how adaptable is it for the future?
So adapting sort of like a ground source into a house that's had gas. Is that what we're sort of talking about? Is that the sort of...
I'm not sure. Stuart, do you want to take yourself off of mute and give us an idea of what the question is?
Yeah, sorry, I'll explain that a bit better. If, for instance, you wanted to add an extension to the house and it happened to go over where you've put your ground source pipes and stuff, how can you adapt them?
So are you saying that if you put an extension on your house and you've got some bore rolls out the back?
Yeah, you put your system in and you decide, somebody comes along, I want to extend this house or whatever. I mean, looking at your diagrams, it was quite extensive, the system.
So if you was gonna put an extension on your house,
yeah,
and have you already got a heat pump fitted already, or do you want to fit?
You come along to the original house, you put your system in, somebody else comes along, or even the same owner, decides he wants another 20 bedrooms, or a bedroom or two.
Well,
you want to extend, can you?
Well, you better put some more borehole in there and another heat pump in. If you're going to put another 20 bedroom or another 5 bedrooms on there, you'd either if you had an existing boiler already in there, Stuart, and somebody wanted to put another 2.
Cross purposes here. It's not extending your system, which I would expect you'd have to do anyway. It's like foundations, getting foundations in for the extension and things like that.
So you'd have to make sure that wherever you put your boreholes on the site visit, in the future, if you thought you was going to extend your property, you would keep them away from that extension. There is boreholes underneath buildings, but as long as they're headed off at least 2 meters depth. So the possibility is there, but it's up to you to understand that in the future, if you said, I've got 2 boreholes here, I want to be able to put an extension there well, I wouldn't do it on top of 2 boreholes that weren't designed to have an extension on top of it.
Right, so that's big, and presumably then you could then adapt your system to case for the extra bedrooms or whatever.
Well, the thing is obviously if so let's say for instance you've got a 4-bedroomed house and you said, oh, we're going to have another 2 bedrooms on this, and your boreholes are designed for 4 bedrooms, then you would not be able to do it unless you put another borehole in there at least.
Yeah, and you can do that though.
You can put it on there, but the disruption would be great. Right. You would have a large amount of disruption, but you can do it, yes.
Right, so it's feasible but not practical.
Correct.
Right. Okay. Thanks.
No, okay, another question in from Ken here. How are you planning to monitor ground temperatures in the borehole ground loops? I think you touched on it, Andy, didn't you?
Yeah. So actually, what kind of key thing came about is for some time now. I've been interested in what actual ground temperatures are, because when you speak with BGS or any other guy who's done a software based on that report, it's normally based on 9 or 14 degrees, which is too much of a variable. You cannot base physics on a variable. It just doesn't work. So I've developed along with actually a couple of guys who did some stuff at Salford, Nigel. They done the software and the hardware for me to be able to put the sensors on and record the temperatures from them sensors. At this time, you know, I've got them in systems that I've got boreholes at 140 meters depth. And interestingly enough, the system does also map into the heat pump as well. So I can see what the incoming electric is while I'm using it. I can see what the compression cycle is on the compressor while it's doing it. I can see also external temperatures, outdoor temperature, and I can see indoor temperatures. Now, yet again, we need to know what the heat pump's going to run at that time and if the ground can sustain that temperature. So I couldn't see anything that was out there that was working on live working systems. Unfortunately, I haven't got the money to go around drilling boreholes up and down the country just to see what temperatures the ground is. I can't get a driller to do it for free or at 10% cost. So I tend to put them in with live working systems, if that answers your question, Ken. I'm quite happy to talk with you about that if you needed to, Ken.
Yeah, we'll maybe take it offline, but that's great. Thanks very much. Hopefully it's not just you and me, Andy, that are trying to convert all these good folk that are listening in away from the follies of air source heat pumps over to proper heat pumps that go on the ground, especially if you know, you're on granite like we are here in the north of Scotland.
Yes.
And you know, I just spoke to a guy in the breakout room there in Devon. The same thing there. It's just a no-brainer if you are on rock. It's just the government has made it so difficult to get funding. They need to change. But anyway, that's my rant over. Thank you very much.
Yeah, and you're dead right. Just before you go, there's a fudge on a fudge, isn't there? So a heat loss calculation that might have a 10% fudge. And then you'll have a ground loop design that might have a 10 or 15% fudge because the designer is worried about it all going wrong.
Yeah.
So
if we can monitor these figures, then we can reduce the cost of boreholes so that, you know, they become sensible rather than, as you say, just, you know, they keep adding on, you know, just factors to prevent us getting something that won't work. And it just, as you say, it's on and on and on.
Correct.
Thank you.
Probably got time for one more question.
Sorry,
Richard
Nigel.
George is here. He says, also, you mentioned slinkies. I see Kenza specify them, but you seem to be a bit negative towards the use of them.
Okay, then, slinkies. Okay, so it's whatever your preference is. That's my sort of political stance on it. Personally, I never do them. I use a straight pipe, flow and return, straight in and out. If guys want to take the chance on shallow geothermal based on their abstraction rate, that's down to them. You know, I know Kenza use them. I know they like to use them. Also, Kenza use static scroll compressors, not inverter driven. So it's however they're designing their system, but not for me. It's not the thing I like to do. But sorry, guys. Yeah, so that's my take on it. Personally, I wouldn't use them, but that's me.
Thank you very much. So there are a couple more questions, but we'll leave them so we can move on. If is it okay, people get in contact with you directly, Andy? You've left your information there.
Yeah, anytime you want, guys.
Brilliant. Thank you very much. Great. So now we move on to, I've got it as down as district heating, but I've been told emphatically, no, they're now called heat networks. And I should know that because I have been involved with heat networks in the past. So we've got from Vital Energy, Gemma Dyson and Glenn Harrison. So Gemma has led Vital's bids for successful low carbon energy schemes at Paddington Village for Liverpool City Council, University of Keele, which I know has got some very interesting stuff going on with utilities in general, University of Sheffield, University of Edinburgh, and Glenroth's heat network for Fife Council. And then Glenn's going to talk about working with heat net operators and suppliers to identify opportunities for network data management and consumer management platforms, which is very important in this area. Access to performance and operational data from network assets helps shape consumer behavior and drives efficiency in the system's operations. So Without further ado, I don't know who's going to come on first. Please get the show on the road. Thank you.
Thanks very much for the introduction, Nigel. Can I just check everybody can see my screen there? Is that come up there? Yeah.
Yes, we can. Thanks.
Okay, great. So I'll kick us off, and then Glenn and I will do a bit of a Chris Whitty and Boris Johnson bit where he'll ask me for the next slide. So bear with us because we are in different rooms within the same building while we try and get this done without any terrible echoes and things that are the joys of Zoom. So thank you for inviting us to present. We're both from Vital Energy, so district heating company by trade, by origin, been around for over 30 years, and district heating and heat networks are what we do. We do a lot more than just put pipes in the ground now, and hopefully we'll cover some of that in this presentation today. But we have worked on some of the oldest heat networks in the UK, such as Sheffield and Nottingham. But having worked in the industry for so long, we have seen it evolve over the last 30 years from coal to gas, and then from gas CHP to heat pumps and other emerging renewable generation sources. So if we'd have been doing this presentation 4 years ago when I joined, we'd been talking about how many CHPs we'd installed. Now we're talking about heat pumps, and very much led by the market and technology moving on. So we are technology agnostic. We'll get heat generation from wherever we can. Our clients are predominantly universities, hospitals, local authorities, so predominantly public sector, but we do some big industrial schemes as well. For those of you who don't know us, we're based in Blackburn in the northwest, so that's where our head office is, but we do cover the whole of the UK, and we've got offices in London and Scotland. So a brief kind of Vital by numbers. We've got 7 heat pump projects in development at the moment, which doesn't seem like a big number, but when you think of the size of some of those, we've got one of the UK's largest water source heat pumps going in up in Scotland at the moment. I'll touch on that later. We've delivered loads of biomass projects. We've installed over 140,000 metres of district heating pipe networks. And we also, which is a bit of our business that people tend not to recognise or know as much about, is that we do have over 36,000 heat customers. So we are metering and billing customers in heat networks across the UK. So we do have access to metering data and some really good information that helps us in the cycle of designing, building, operating and maintaining heat networks. That little bubble with the carbon savings at the moment, obviously a huge market shift towards decarbonisation and net zero, and local authority partners in particular looking to reduce their energy consumption. So we're doing a lot of energy conservation measures for various clients and trying to help them save money on electricity and gas bills, and also decarbonise their estate. So working with a number of clients, particularly large hospitals, universities, to try and help them reduce their carbon footprint. And that's sometimes through heat networks, but sometimes through other things like solar or double glazing, insulation, changing your lighting over to LED. So we do the full hit of that. So briefly, what we do is design, build, operate, maintain heat networks. So we do get involved in all those stages, which are shown on the slide there. We can also bring funding and financing to our clients. And we're quite well known for that, I would think. Like I said, the asset management and end bit, which is a bit that Glenn will touch on, is probably the lesser known side of our business, but we do offer the full one-stop shop. We do offer those services individually as well. We've got a team of in-house designers that's about 70 strong, so we've got a big design team in-house who design those schemes. We then build, operate and maintain them. Also, something that I'd just like to mention is that we are constantly investing in the future as well, and we've recently, even though it's been the chaotic 12 to 18 months it has been with the COVID pandemic, we have just built our own training academy at our headquarters in Blackburn. And we're working with Liverpool City College to provide 20 apprenticeships from September this year. So there'll be 10 craft and 10 technical apprenticeships, specific apprenticeships around heat networks. So we're calling them net zero apprenticeships. We've done quite a bit of publicity about that, but we see that as really important because there is a skills gap in this area, not just heat networks, but the whole zero carbon agenda. So we're trying to engage with the net zero workers of the future to try and protect the future and get the right skills that we need to grow our business. Oops, sorry, wrong slide, went too fast. So this little video that will just run while I'm talking here is actually a screen grab from our new website, which we've been trying for a long time to put on a piece of paper what Vital Energy do in one diagram, and that's quite difficult. But this kind of map shows you all the different things that we do. So it takes you from energy generation and storage through energy distribution to supply and consumption management. So, for example, we've just invested in our own energy from waste plant, which is at Drakelow in Burton-on-Trent. So that will burn household rubbish and will use the waste heat in a heat network, supply low carbon heat to people across the area. We get involved in distribution, the actual heat networks, the pipe in the ground, and then we do energy supply consumption management, where we look at how people are using their energy and help them to reduce their carbon footprint. So in terms of what generates the energy, it doesn't matter to us. We can work with anything. It has moved on. It used to be all kind of CHP. We've done over 97 CHPs, but more now we're looking at energy from waste, heat pumps, whether that's air source, ground source, water source, gas boilers, and solar PV is another growth market for us as well. So feel free to have a look around our website and find out more about what we do. So in terms of journey to zero carbon, big priority for lots of our customers, and we try and work with customers to help them on that journey, which usually starts by looking at what they're doing currently and then working with them to work out how they balance what we call the energy trilemma. It's quite a well-termed phrase now, but how you balance energy security with sustainability and affordability, because we see that as the challenge. Everybody wants to get to net zero, but it's not always quick and easy to do, and it's certainly not always cheap. So we will look and do the modelling with our clients to work out how they can get to that position as efficiently and quickly as possible. So we've worked with a number of clients using public sector decarbonisation scheme funding. So I'm sure lots of you will be aware of the PSDS funding that was announced by government earlier in the year, and they awarded £1 billion of funding. Vital Energy are actually involved in delivering about £100 million of that, so about 10% of that fund, which is really good. It's also keeping us really busy because the deadlines on spending that funding is later on this year. So some really exciting projects coming out of that. So I'm going to focus on just a couple of key case studies. It's really hard when you've got a company with such a varied experience across heat pumps and different heat networks to pick just a couple for a short presentation like this. So I've gone for one in Scotland and one in England, and I've gone for a water source and an energy from waste, but there's all sorts of case studies that I could talk to you about quite passionately. But Queen's Quay Heat Network is up in Clydebank, so on the banks of the River Clyde in Glasgow. And it's a regeneration site transforming the former John Brown shipyard from an industrial area into a vibrant, diverse and architecturally engaging community. So it's a 23 hectare site, it's massive. It's going to create 1,000 private homes, 200 rented homes, and then there's health centre, care home, commercial and retail facilities. There's also existing buildings on the site. So the project's groundbreaking in lots of ways. But one of the truly exciting aspects of it is that it features Scotland's first major water source heat pump. So it's taking water from the nearby River Clyde and pumps it to customers through a system of a very district heating network. And what's been really important for us, it's been a massive learning experience for everybody involved, because it is the first of its type and the first of its scale. So it's 2.6 megawatt ammonia water source heat pumps that are going into the scheme. And it's the River Clyde, so it's tidal, it's salt water, and there's a range of both plant and aquatic life. So we've had to take all that into consideration during the design. So the other thing being that there were existing and new buildings, so the temperatures in those buildings were all over the place. So we've had to really carefully plan that scheme around the existing and the future buildings. So we've gone for efficient district heating, and the temperatures are based on 75 degree flow and 45 degree return. And then the second case study is Leeds Pipe. So I don't know whether people will be familiar with this scheme or not, but this is one of the UK's largest district heating networks, and connects 1,983 homes and businesses to low carbon heat and hot water. So in Leeds, just outside Leeds city centre, there's the RERF, as they call it, the Recycling and Energy Recovery Facility, which is their a Veolia plant where they burn their domestic waste. And the scheme that we've constructed with them is takes the steam created at the RERF and then converts it into low temperature hot water, feeds it through 16.5 kilometres of district heat network, and supplies heat and hot water to 26 social housing apartment blocks, but also the West Yorkshire Playhouse and other commercial buildings. We've also built an additional energy centre for backup resilience, which is at Saxton Gardens. And then we have gone right through with putting the HIUs into the social housing flats, because the flats will have to be converted from electric heating to wet heating systems with heating space units, and then our metering and billing monitoring technology, which Glenn's going to talk you through. So it's been a really big scheme for us, a lot of social investment in terms of local people employed, tenant engagement, social engagement, and reinvestment in the Leeds City region. So we've invested 60% of our project spend back in the local area, because that's been really, really important to Leeds. So I'm going to give you a pause from my voice for a minute and just show you a short video on the best practice of district heating at our Leeds scheme. Hopefully it will play okay, and you can just watch that for a couple of minutes, but if there's any issues, just let me know if it's not working. Okay, and I'm going to hand over to Glenn now to take us through the metering and billing and our glass app.
Yeah, thanks very much, Gemma. And yeah, thank you very much for the invitation to come and talk to you today. My name is Glenn Harrison, and I'm going to walk you through some of the digital interfaces that we've introduced onto our networks over the last few months. 12 months ago, Vital launched the Glass digital platform. This was after a period of consultation with some of the largest UK social housing heating network operators and local authority network operators. And combined with our own 30-year experience of managing heat networks, has shaped the Glass platform into being a very user-friendly data collection repository for all things in relation to heat network management. The system itself has at its core a meter and billing capability, but it's developed into much more than that. So the Glass platform collects data from network connected assets. So that could be from the heat interface unit installed in a flat, which essentially looks like the boiler we'd see in a conventional home. It takes the data from heat meters and from any pay-as-you-go devices that are connected to the platform. We can also accept data from the BMS system that might be installed in plant as well, so we can get a whole property view of what's happening within that installation. The data is displayed very simply, so we've got a very simple dashboard. The technology is agnostic, so as long as we can get a very clear file format, so things that you would get from a normal CSV type output from a BMS system, we can basically manage the platform based upon that data. So we manage the platform from both a customer and end user perspective, but we also have the ability to deliver very detailed analytical information for use by the operator themselves. So for the homeowner, the Glass platform has two very distinct front ends. So for an end user, they will be invited to download the platform or download the application from, where the user get their apps from the Google Play Store or from the App Store. Once they've downloaded the application and put in some of their account details, they'll be able to get an overview of their account, so they can see how much energy they're consuming, what their usage is like, look at that historically. So the customer has some very clear information on how they are using their energy that's been put into their property. The customer can also then have some very detailed controls. They can make payments into the platform. They can control and schedule heating and lots of other things that you can now do with things like the Hive platform from British Gas. The operator also then has extended capabilities. So the operator can see the flow and return temperatures that are passing through a system right down to an individual resident level. So the operator can then go down to the platform and they can see where the flow temperature is, what the return temperatures are, and whether those temperatures are in line with the system design. So we get a very, very simple overview of how that network is performing. This allows for very simple and easy diagnostics where there are maybe network issues in terms of actual performance and whether that network is performing in line with its design parameters. From a social housing operator's perspective, they can log onto the platform and they can look at an overall block view. So they can log on, look at the tile that they've got for their particular developments, and they can see a graphical representation of how each and every customer on that network is using their heating. That will give you a very quick, instant visual reference to those customers that are using far more energy than the average. So we can see what the average peers are using. We can see the high users and we can see the low users. The social housing providers love this because it allows them to identify those customers that might be in need of potentially additional support. So you might have some users of energy that are using significantly more than their peers. So there may be an education issue. There may be something, there may be a conversation that needs to have with that customer about how they manage and control their heating systems. It might be something as simple as, is there a bypass left open in that system as well? So we start to do some fairly detailed performance analytics at that particular point on the network. Conversely, we can also start to see those consumers who are using significantly less energy than their peers as well. So from that point of view, we can start to ask those questions, and look to identify potentially those vulnerable users on a network. So it might be that those customers may be at risk of fuel poverty. So again, the housing association or the network provider can start to identify where they need to point the additional support services to ensure those customers have the support that they need when they need it the most. Access to performance data in this way allows us to get a very clear insight of how the network is operating. Once we've got that, we can start to look at how we shape our future design. So a network that we design today will have taken in massive amounts of data from networks we previously designed, and we have the visibility of how it's actually performed in reality. When you look at network design, you've got your CIBSE guidance, which is fantastic. However, there is nothing better than real life data from real life sites. You can start to get a true picture on how the networks will be performing and how those customers are actually interacting and using the systems. I said that Glass was much more than just a metering billing platform. When Glass is actually added into our vTherme range of heat interface units, it brings Hive-like capability to that customer. So that customer has the ability to control their heating, so can turn it on, turn it off. I think the Hive advert shows them down the park, and they're at the park and they're all cold, and they can turn the heating on remotely and make sure the house is nice and warm by the time they get home. You can do exactly the same with the Hive with the Glass capability built into the HIU. The customer can also then manage their account, make payments, and turn the system on and off. as and when they want to do it. But equally, the fact that we can communicate with that asset remotely means we can also understand how the network is performing. We can also look at how the network is performing in terms of its initial design. So if we identify by exception where potentially the network has a higher return temperature or a lower temperature back from the assets, we can start to look to tweak that performance. So we can dial into the individual assets, manipulate it, so the system always comes back to its optimum design performance, and then is always performing to its, its key, performance and financial caveats that are on the system. If we can't manipulate that device remotely, the data we get back from the asset allows us to identify what additional works may be required. So if we need to go and fix something remotely, it means our engineering responses are very targeted. So we know exactly what spare parts to take, we know exactly the nature of the problem. So in terms of a customer journey, the level of inconvenience to that customer is massively reduced simply by the virtue of the data we can get back from that particular asset. In the actual platform itself, we've also introduced individual communication modules into the heat interface units. This means that the system can either be operated as a credit billing unit or as a pay-as-you-go unit. And should the customer get into financial difficulties, we can manipulate their accounts appropriately in line with what their customer service agreements are and the operator's consent. The system, the fact that it has its own inbuilt comms means you don't need to go away and buy separate communication hardware, and you also avoid the need to install M-bus cabling through the blocks as well. So in a retrofit environment, you simply have less work to do and less invasive work to do when you're looking at refreshing or replacing the heat interface units that might be installed on your network. So again, we're looking at reducing the capital requirements down whilst increasing and enhancing your capabilities. We've got a short video now which will run through some of those capabilities. If you can press play, Gemma.
Vital Energy provides secure, reliable, low-carbon heating and hot water via heat networks to over 83,000 households throughout the UK. And we're committed to providing high-quality smart technology to deliver exceptional customer service. Our V-Therm range of HIUs are a compact, economical alternative to a traditional combi boiler, which connects your home to the network and gives you reliable, instantaneous heat and hot water on demand. Based on market and customer feedback, we have developed the Glass app and portal. This smart app gives you visibility of energy usage and control of your energy spend, whilst allowing you to make quick top-ups or bill payments from the comfort of your home. And when coupled with the V-Therm E, you can also schedule and control your heating in the app, monitor your energy consumption, view your usage and payment history, and best of all, you only pay for what you use. Glass takes accurate meter readings. And when it comes to paying your bill, with the Glass app, you can do this in a few simple clicks. If you're a pay-as-you-go customer, we have a variety of payment methods, so you can choose which is best for you. Wherever you are, you'll always have instant access to your account information, bills, and balance. Should you need answers quickly, you can use the Help and the FAQ section on the app or portal. And if you can't find what you're looking for, our customer service team are always on hand to help you. Our nationwide engineers undertake routine plant maintenance at our energy centres, ensuring you have a constant source of heat and hot water. And our team of specialists ensure that not only is our plant operating at 100%, but so is your HIU. As part of our service commitment, we'll come and service your unit every 2 years. We look forward to welcoming you to the Vital Energy family.
Cheers, Gemma. So whilst the video focuses on the end user requirements from the application and the control of the assets, what we do get from the data that we collect is a complete understanding of how a network is performing, get complete visibility of, of what we can do on that particular project to improve performance, to improve efficiency, drive down those running costs, and obviously increase the carbon savings that we can make in a network. Access to good data is absolutely critical now going forward. we've now got a case study here for our site at Uncle Wembley. I'm not entirely sure why it's called Uncle Wembley. I'm sure there must be a very valid reason for it. And maybe the neighbouring site is called Anti Wembley. But on this site, it's a large-scale residential development down in central London. And we installed glass as part of the installation programme on the project. From that, we're getting very detailed information in terms of user performance. We're able to see exactly who's using what energy. We have much closer communication with the customers as well. So we've had occasion where the energy plant has had to have some maintenance on it. We can send a notification to all those customers in one go. So that means that there is a much broader ability to communicate with the customers, to notify them of future works. And the housing associations can take advantage of that and communicate directly with their customers. So it keeps everybody informed. We can also see very clearly, those customers that are have higher account balances, lower account balances, and look at the trend information that identifies those customers that may be in need of that additional support that can be offered by the local authority housing provider and some of the support institutions like the Advice Bureau. So again, it gives us that ability to understand how people are managing and how people are coping. The platform here also has the weather capability built into the platform as well. So the platform here at this point looks at local weather conditions that are prevalent to that site. It looks at the customer's account balances, and it tracks the level of usage based on the temperature and the prevailing weather conditions, and basically tracks them, how long that credit will last given the increased use on particular cold spells. So again, it allows those customers to budget and puts them back in control. So the feedback has been superb from those residents and those customers that are using the system. The housing providers also have full detail of the network operation. So again, we can start to understand how the system's performing against its design parameters. So again, we can start to look to manipulate that design and that performance to ensure that it does meet those financial caveats and those design parameters that were initially set up for the scheme. So Uncle Wembley has been operational now for over 8 months. All the users now are signed up to the scheme. So we are offering this scheme the full metering, billing, and O&M capabilities as well. So because we have access to the data and the performance that runs through right down to individual plot level, where we identify anomalies in performance, we can also stimulate the engineering responses as well. So we've basically got a full end-to-end solution. So should we notice any deviations in the network information, we can target the engineer's response. So in most cases, we've already attended and fixed the problem before the customer's actually aware that it's existed in the first place. So again, it gives us that ability to be proactive with maintenance. It gives us the ability to be proactive with site services. Customers also have the ability to do the full account management in this. They can see their own consumption, they can see their own spend levels. The fact that everything's now online and accessible through either the application or through a portal also means that their engagement with their energy is far more increased. And on this site in particular, our customer service calls have dropped down by over 60%, simply because the customers have access to the level of data that they previously couldn't get access to. So most of the common questions that you would have about a heat network performance, my own billing performance, how is my heat consumption compared to my neighbours, all that information is there to hand, along with some handy hints and tips on how to improve the efficiency of your system. So again, access to data is influencing how we manage our customers, the information that we give those customers, and hopefully improving that customer journey and the control that they feel when they're working or living and occupying properties on a heat network. I think Gemma is at it now.
That's us.
Yeah, and on this picture, I appear to have turned into my dad, so that is a worry.
Thank you very much from the double act there, and we can see Glenn there, and behind him, right above your head, is a wall-mounted air source, air-to-air.
Yeah, it's only because my background didn't work.
No, it's good to see. It's good to see practically there's something there. And we've got one question that's come in there. Gemma, someone was interested in the video that you showed, and you mentioned it was on the website, but they couldn't find the link. Could you pop into the chat the URL for that, the link to the video? Great. So again, thank you very much. And I'll move on to the next speaker, which is me. Unfortunately, you've got me. I'll give a little background of myself. So previous to, I'm working at Energy House 2 now. Previous to that, I was working at the District Network Operator Electricity Northwest, looking at their carbon reduction in their own operations. And one of them was the Zero Carbon Training Centre at their Blackburn centre there. So they're trying to make that net zero. Previous to that, I was heading up the renewable heat side of the National Trust's renewable energy programme. Prior to that, working with Cheshire East Council, which involved deep geothermal, but really, you know, the bulk of my career has been in biomass heating, originally coming from a forestry side. So you will get probably a bit more about burning stuff because I'm a boy and I like burning things. So right, if you just bear with me. Are we okay, Ruth? Can we see the main slide?
Yeah, that looks fine. Thank you.
Great, super. So yes, I'm going to touch on all these things. So you have seen or you have had information currently about air source. You've had something about ground source. Sorry about the use of the slinky things there, you know, Andy. Had a little bit just about the heat networks there. So it's my job to do the mopping up, I suppose, on the low carbon heat side. So like I mentioned, I'm going to start off with what I really enjoy is biomass. So what is biomass? Well, essentially biomass is anything organic, whether it's animal or vegetable, but it's certainly not mineral. And in terms of what we're talking about in this sort of retrofit and particularly the domestic retrofit sort of arena, we're generally talking about wood. Now, wood is a fuel and fuel have three distinct properties. The first is it can be produced somewhere else. So here we've got grown in a woodland and then it's cut down. It can be transported to another area and it can be easily stored for use, and then it's obviously going to be burnt. Another three things about how does it burn. Sorry about this is just me and biomass. So you need three things. You need the fuel, which is the wood, you need oxygen, and you need a means of ignition. And this, I guess, is most shown fairly well in someone lighting a cigarette. So the fuel is a cigarette, the oxygen is around you, and the means of ignition is the cigarette lighter. And again, the rule of three, the combustion process. So the combustion, the actual burning of the fuel, any fuel really, has three sides. So the first side is the drying. This is driving off of the moisture. And secondly, you get the combustion of the volatile gases, which produces that lovely flame that we all love. And lastly, it's the sort of the glowing char and the embers. And generally, again, another three, the fuel formats for the sort of domestic sector with biomass is logs. We also have wood chips. I could have put a picture of chips there as well. That would have been very northern. Or we can have wood pellets, which are basically compressed cylinders of sawdust. There is a big difference though between this and the other sort of fossil fuels, and that's down to kind of like fuel and energy density. So, you know, the high density fuels, the fossil fuels, you can get into a small space, whereas the woods and things, it's got a low energy density. So what we do need is space and lots of it. So that's a kind of disadvantage there. However, what we do have is the infrastructure. So again, looking at retrofit, we have the infrastructure for combustion in the form of chimneys and flues. Not often in these old properties, we have some kind of storage in the basement, unless we put some kind of gym or something down there. So there are some of the advantages there, but there are disadvantages, and that is principally down to air quality. So in 1956, we had the Clean Air Act, and link back to Salford. Salford was the first local authority in the UK to produce a blanket smoke control area. So throughout this area, throughout the whole of Salford, it's not just certain roads or whatever or postcodes. It's often done on in some local authorities, the whole local authority, there is a smoke control area. So within these areas, if you do want to burn something, you have to have a approved fuel. There's not many approved wood fuels, or more often than not, it's an appliance. So you have an approved appliance that's been tested to show that it burns efficiently, it reduces the amount of pollutants, so it's got reasonably good air quality. It's also worth bearing in mind that there is its own building regulations, the approved Part J document. I would draw specific attention to air supply. Now, obviously, we're looking at retrofit, the whole fabric first thing. We're looking at air tightness. Now, the problem is the more airtight you make the property, the less air there is. And that's one of the three things, wasn't it? The oxygen that you need. So either you're going to have a dedicated separate air supply that goes straight into the stove, or you're going to have to accept the fact that you're going to have a leaky property to allow that in. So I've got a wood stove, for example, and one of the key things I keep saying to my partner is don't switch the extractor fan on in the kitchen when the fire's on, because that will cause a negative feedback there. So in the domestic situation for just log stove, we like to see three types, which is the sort of classic standalone log stove up in the top left-hand corner. Below that, we have something called an inset stove. So this fits flush into a British standard fireplace usually. And on the right-hand side, a Rayburn, which I lived with one like this for many years. But obviously, not only does it do some space heating directly from the radiance there, you could do your cooking on it, plus some of them will have a small hot water boiler in the back. I won't touch on wood chips, because it's probably not suitable for a domestic situation, but I will touch on pellet stoves. So here you can see the pellets. They usually go into the top, so manually fed with a bag of pellets into the top there. These are fairly readily controlled. They pump out hot air. Some of them will do hot water. You can program them on a thermostat. I even was involved in putting one in over near Warrington where we could text it, which was great. You know, when we were doing things, particularly educationally with younger people, you could text it to go, you'll get them to text it to come on. And a lot of them do have their own dedicated air supply in there. So there's none of the issues there. But a lot of these are, you know, you'll have to fund these yourselves. When it comes to the domestic RHI, we're looking at systems that do really produce hot water for the whole property. Now, here is an example of what I would call a smallish system here, but you can see, and I think it's good that you can see that vehicle there. So I don't know whether that's an Igo or a Toyota Yaris, but you can see that the pallet of wood pellets there, the larger sort of box structure on the left-hand side is the hopper for the fuel. The one next to it is slightly smaller, is the actual boiler, and the little box on the floor is the ash. So you can see, one, it takes up a lot of space, and two, you've got a little maintenance thing there. You've got to unhook that little box of ash and empty that every now and again. All that's not too much hassle. So that's it for biomass. Quickly move on to solar thermal. So I don't know too much about solar thermal. I know that if you want any questions, Nathan and Andy have got a lot more experience on this, but I will say that it's probably the Cinderella sort of low carbon renewable heat technology. Works fairly simply. You're absorbing sunlight that goes into the hot water tank, circulates around, fairly simple. Give you a rough idea here. We've got a roof on the right hand side, we've got some solar PV, and in the bottom left there you can see that there is the solar thermal. These are evacuated tubes. Moving over to a little diagram here, I'll show this just because, you know, talked a lot about a tank, you need a tank, but this is a twin coil system. So Up the top, you can see the solar thermal panel will be producing hot water, and principally you can say that it you know, if you size it right, a metre square or a little bit more per person will provide almost all the domestic hot water in summer, a good amount spring and autumn, and may have some benefit. But then you'd link in the boiler as well for the hot water during the winter season. Again, it would link in. Biomass works really well with this sort of a small biomass system, and solar thermal works very, very well. A couple of types of solar thermal panels. You have your flat panel, which is basically, you can see the sort of dark coloured, which is the sort of absorbent material with pipework underneath and insulation below that. And that's basically just absorbing the hot water. The other type is these evacuated tubes, which you've seen the picture of before. It's basically a vacuum with the fluid in here and heat exchanging going up on in the top of the system. And this doesn't, you know, the two types, I'm told that there's not much between them really. But again, someone like Nathan can correct me about the precise nature of what's more efficient. But what is interesting is that, you know, linking back to the heat networks, is that this is on top of a exhibition centre in Austria, where the solar thermal is providing a lot of the hot water during the summer months. So you can deploy it at a larger scale. Okay, now I think Dave's dropped off, unfortunately. This is the contentious bit, green gases. So we'll start with the non-contentious green gases. So we can generate green gas from anaerobic digestion. So this is the digestion of organic material in the absence of oxygen. It produces a biogas, which consists of methane and carbon dioxide. So you sort of clean that gas up, remove the carbon dioxide out of there, do some more scrubbing. You can inject that directly into the gas main, or you can use it for heat. In this case, it's running a generator set here for CHP. So that's one source of a green gas. The other source is what we call a synthetic gas from gasification of organic matter like wood. And you look at this and you think, oh, that's a complex situation. We can't possibly do that. But this is exactly the same as we produced coal gas when we, before we rigged up North Sea gas to our gas network. This is exactly how we produced the coal gas, and then we stored it in the gas in the big gasometers. So the biomass or the biomass material goes in one end. It is combusted in with very little oxygen in there. So that volatile gases are produced, but they don't ignite. And then out of that, you get the char material. So I guess in the old coal situation, that would have been a coking coal, but you know, we get a wood char or a biochar, as they call it now. Again, that's it. And then we have hydrogen. So yeah, I know low carbon heat, it's all about electrification. So why are we talking about green gases and hydrogen, particularly if, you know, if you've got spare energy, you put it into a battery, surely. But, you know, I guess it comes down to the fact that we've still got 80% of homes connected to gas. And yes, we do want to electrify, but there's also a lot of gas infrastructure already in place. You know, there is this thing with radiators. Dave has mentioned it's not too bad, but, you know, there will be this thing. Do you want to put more or larger radiators in? There are hydrogen ready boilers. And I guess it comes down to, you know, the gas network companies have a large amount of assets invested in the ground. Are they going to take this line down? I don't know. But as Dave mentioned, there is a sort of fledgling gas network in hydrogen gas network in the northwest here, mainly supplying industrial processes. But it does work at a smaller scale. I'll have a chat with, if Nathan's not come across this one before, I'm sure he has. This is in Cheshire. So this is a farm which has, so there has a wind turbine there. It also has quite a bit of solar thermal. So what happens is that is used directly on this sort of farm and industrial, sort of small scale industrial units. When there is excess to what's being directly used, it's then put into a battery bank. When that battery bank is then full, it's then put into, you can see on the right hand side there, that's like a half container size. That's got in there a hydrogen electrolyzer. So that produces hydrogen, which is used to power the tractor and a forklift on the site. But more interestingly, it goes into a catalyzing hydrogen boiler, produces low temperature hot water, and is fed around the site in a mini district heat network. Deep geothermal, as Andy said, the normal ground source heat pumps, the geothermal energy is coming from the sun. With deep geothermal, it's coming from the core of the earth, and that happens all around the country. But there's certain areas that are particularly good, and you can see ringed there. We have what we call the Cheshire Basin. That's particularly good for geothermal heat. So in this area, Manchester, Cheshire area, the heat will be sub 100 degrees. This is a picture of which will be a heat and power plant being developed in Cornwall. So if we look at the split diagram there, basically you would have usually a twin bore, or that can be a single coaxial well being drilled down, and the heat collected. But look at the distances there; they are pretty deep. So it's ludicrously expensive to drill holes. There's still risk from geological anomalies. However, deep geothermal was looked at by E.ON in East Manchester. I was involved with Cheshire Council looking at a scheme in Crewe, but it involved a 4-kilometre deep borehole, was exceptionally expensive, so that didn't work out. Another shallower scheme was looked at in Crewe for Manchester Metropolitan Campus there, and I think that was a hybrid system with a heat pump. Gemma will probably know, I think Keele were looking at a hybrid system using mine water as well. Sort of finally, it's kind of far infrared. So what am I talking about far infrared? Is this low carbon heat? Well, I guess with the electrification, it will become low carbon. It's certainly not being pushed policy-wise, but certainly we're hearing about it all the time. And at the university, we get sort of people coming with ideas through the gate all the time. And the one thing that everyone's talking about is this far infrared. So we'll talk briefly about it. So what is it? Well, basically, this sums it up quite nicely. You can see it's obviously very cold there. It's snowy, but that person is feeling the heat from the sun. So that's the invisible wavelength far infrared. Our security lighting detectors, most people have at home, work on a similar wavelength, but it's very different in that it heats up things and not the air. So what you can get is thermal, it has some advantages. It can be unobtrusive. So here we can see panels situated on the ceiling, or you could disguise it as a picture. That's a panel there, or even in the bathroom behind a mirror. And we've seen stuff coming in now using thin graphene films in a mat that you would place on the floor. So that's the very brief mopping up there. So any questions that people have? So I know that, I'm surprised that there's someone's got to have a question about, surely about hydrogen. I know, like I said, if Dave Kemp was here, he'd say something. Mark Collett says, hi Nigel, with biomass, is there a good blagger's guide to how sustainable the fuel is produced? Yes, there is. There's, I guess, what you want to look for any of the wood is the Forestry Stewardship Council or the PEFC, it's Pan-European Forest Council brand on there. With regard to wood pellets, one of the key things you want to look for is the EM Plus A1 mark. and that's certainly good. There's been recent legislation coming in the past couple of days which says, or will become force, it says any bagged logs, for example, must be kiln dried. Not quite sure how that's going to be enforced, but we'll see. Okay. Victoria says, which of the alternatives to electricity do you think have most legs to become widely adopted in the near future? It's got to be heat pumps. I mean, there's no doubt about that. I mean, they're a lot more, you know, with the coefficient of performance, they're a lot more energy efficient. Any more? Okay, I think we'll leave it at that for the time being. If anyone has questions, get back to me. This is being recorded. It may take a couple of weeks before we get everything, because we want to put the whole series online at the same time. But we will inform everybody. I'd like to thank the speakers. Thank you very much. It's all been very good, and like I said, I'm sure that these everyone that's spoken will be available if you've got any more questions you want to ask. Like to do a final poll. So Ruth, can you put the polling questions up, please? So question 1, how much has your knowledge of low carbon heating improved? From a lot to hardly any, and I don't know. And then what do you think will be the main barriers to the electrification of heat? So with the first one, you can just do one question, yeah? With the one answer. With the second one, you can put multiple ones in there. So please click away. So when that's ready, Ruth, could you, when you think you've got enough results in, can you display that screen? Oh, okay. So how much did knowledge increase? So a moderate amount. So people have learned quite a bit there. What do people think will be the main barriers to electrification of heat? Quite interestingly, reluctance of householders to undertake plumbing changes is well in the lead there. So that's interesting there. So thank you very much for that all. So before we close, this is the penultimate webinar in the Retrofit series. We have one more next week, which I think is probably the most interesting, which is about smart homes, smart devices, and how that can improve homes, whether retrofit or otherwise, really. But certainly in the work that I've been doing, I've been seeing at the university, this is the most exciting area that we deal with. So that should be good. And just as a little introduction, it will be hosted by Yanis Paraskivas, and we have a short video which I think I can play, or you can play, Ruth can play that. Yeah, thank you, Ruth.
Good afternoon. My name is Yanis Paraskevas, and I'm running the Smart Meter Smart Homes Research and Innovation Lab. Following today's session on low carbon heating technologies, next week we are going to cover the very interesting area of smart home technologies for energy and cost savings. Next week, we have invited 4 excellent speakers. The first one is Nigel Blandford, who's going to talk to us about the electricity supply network. The second speaker will be Karolis Petroskevicius, covering the area of energy savings on heating using time of use tariffs. The third speaker will be Matt Roderick, covering the area of products and services of the smart home ecosystem, again focusing on energy and cost savings. And then we are going to close with a very interesting session on home energy management systems, who's going to be delivered by Jose Figueiredo, if I pronounce his surname correctly. Looking forward to seeing all of you next week. Thank you very much. Bye.
So looking forward to seeing you. I'll be giving a little talk obviously there next week. So if you thought you'd got rid of me, unfortunately not. I'll be there first thing next week. But without further ado, yeah, let me thank again the speakers for today, and hope you enjoyed it. If you've got any feedback, then please give it to us, and hope to see you next week. Thank you very much and goodbye.